Guten Morgen, meine Damen und Herren. Good morning, everyone. G'day, mate. I'm Jared Cole from RMIT University in Melbourne, Australia. And this is our session on the Friday morning, the tough session. Congratulations, you all made it after some very hearty meal and cheer from the Bavarians last night. Today we will be looking at applications of superconducting qubits beyond computing. This is actually a topic that I quite enjoy working on, simply because there's so many cool and interesting ideas that go beyond just trying to make qubits. Because as we've heard many times this week, there are many, many things you can do with superconducting circuits. So it's my pleasure to introduce Patrice Bertet from Saclay, yeah? Saclay. Yeah. Just had to check. Your slides should come up very soon, I suspect.
Yes.
Unless you have to swap. Does he have to swap? Or?
Yes.
All good. Thank you very much. Please, Patrice.
Thank you, Jared, and thank you all for showing up after a late conference dinner yesterday. So this session is about applications of superconducting qubits beyond computing. And in my talk, I will describe applications of qubits in quantum sensing. And more precisely, to the field of magnetic resonance spectroscopy. And what we've been able to develop by using superconducting qubits is a new method that performs magnetic resonance, but with single spin sensitivity. And the principle of the experiment is shown here in this schematics. So we have, in fact, two devices in this experiment. We have first a spin device, which consists of a crystal which embeds spins. And on top of this crystal is patterned a superconducting resonator. And the spin can be excited and then relax radiatively and emit a microwave photon at its resonance frequency into a waveguide, a coaxial cable. And now the second device in this experiment is this device. And the goal of this device is to detect this microwave photon that is an itinerant microwave photon in the coax. And this is based on a superconducting qubit. And this is a microwave photon counter that we have developed specifically for this experiment. And so I will start by describing this device, this microwave photon counter. And the principle was, so maybe I will start by saying that the principle of the device was invented by my colleague Emmanuel Flurin, with whom I co-supervise all these activities. And so the counter itself consists of, let's look at the counter. So we have this coaxial cable with the photon arriving at frequency omega b. And the device consists of an input resonator at the same frequency as the incoming photon, which is coupled to a transmon qubit at a frequency omega q, which is not equal to omega b, so this is not resonant absorption. And the qubit is also coupled to a second resonator at frequency omega w. So the input resonator is called the buffer resonator, and this output resonator is the waste resonator. And what we do is to apply a pump tone to parametrically induce a four-wave mixing process in which the incoming photon together with the pump photons are going to be converted into a qubit excitation and a photon in the waste mode. So this is this four-wave mixing Hamiltonian. And to make this process irreversible, we have to add dissipation of the waste mode. And by selecting the pump amplitude in order to reach cooperativity 1, then the conversion can be complete and fully efficient and without any added noise. So essentially, the photon is going to be converted. The incoming photon is going to be converted into an outgoing photon at frequency omega w, but together with an excitation of the qubit, which can be read out in a subsequent step. And so this is the device, a schematic of the device. And so we have the qubit at its center, the transmon qubit. The input resonator is coupled to the input line via a pulsar filter to protect the qubit from relaxation, and same thing on the waste side. And one important aspect is that so the frequency of operation of the detector is really this buffer resonator frequency, and the detector is quite narrowband, and so it is important to be able to tune this frequency, and therefore we have a squid inside the resonator that we can tune, and we can tune the frequency over a few hundred megahertz, and therefore tune the detector at the point of the other device, of the frequency of the photons that we want to detect. All right, so let's look at data from this type of device. So what we do is simply to apply the pump tone, and we're going to first look for the four-wave mixing condition by sending on purpose some coherent tone on the buffer side. And so, so we have these detection windows in which the pump and the buffer are switched on, and then we stop them and detect the qubit state. And this detection we do via the waste resonator. And so this is by sweeping the buffer frequency and the pump frequency, we see some, say, excited state appearing at this condition, and this is the four-wave mixing condition, and we can check that if we don't send any photons on the buffer side, nothing happens. So it's not excitation via the pump, it's really the combination of the pump and the buffer that do the job. And so, so this is to find the four-wave mixing condition, but really a photon counter should be operated in a cyclic mode, and it should just go on forever, essentially. And so this is now this cyclic mode, which is really the interesting mode of operation of this device. And so here we have a detection window that, again, consists of just applying the pump, and nothing should happen, except if a photon arrives. If a photon arrives, this triggers its conversion into the waste frequency and the qubit excitation. And so this detection window, we keep it on for 10 microseconds. Then we read out the qubit, and we have a conditional reset if we find the qubit in its excited state. That's in order to speed up, to have highest duty cycle of the detector. And so in this way, we can have a duty cycle of maybe typically 80%, and yes, so with a cycle time of approximately something between 10 and 20 microseconds. So the device is working. So this is, now we can really look at long traces over time. So these are traces over 1 second. And this is when we do not apply anything to the buffer. So these are just the dark counts of the detector. And here we have 85 dark counts per second. Now when we send some photons, we have more clicks, more and more and more. And with this, we can, using circuit QED techniques, we can calibrate this input tone, and we can determine the efficiency of the SMPD itself, and we find it's like 43% in that particular device. And so the dark count rate is 85 per second, and from this you can extract a quantity which is, say, energy sensitivity, and which amounts here to 10 to the minus 22 watt per square root of hertz. And this is actually, to our knowledge, the most sensitive energy detector at microwave frequencies that has ever been demonstrated by probably more than an order of magnitude. So this is the detector. Now let's look at the spin device side. For the spin device, we use a crystal called calcium tungstate, which is shown here. This crystal has tetragonal symmetry around a C-axis, and so two equivalent axes A and B, equivalent by a 90 degrees rotation. And we like a lot erbium. Erbium actually substitutes for calcium at certain sites. And we use a crystal that is actually grown undoped, and this is just the residual doping, the traces of erbium that we can find in the crystal that we will detect. And this is grown by our colleague, Philippe Goldner at Chimie Paris Tech. And so on this crystal, on top of this crystal, we pattern this superconducting resonator, and then we just have a Jaynes-Cummings interaction. We have magnetic coupling of the erbium spin, the magnetic dipole of the erbium ions, to the resonator. And so this is characterized by a coupling strength, G0, exactly like in circuit QED. And this, and then, because of this coupling and of the decay of the resonator towards the waveguide, the spins also have some induced radiative decay, that's the Purcell effect, at a rate gamma r, which is 4G0 squared over kappa. And this decay gives rise to the emission of these microwave photons, and this is what we call microwave fluorescence. This is really just spontaneous emission from the spins, and this is what we are interested to detect in our experiments. And so one nice aspect of erbium ions from that point of view is that they have a very anisotropic gyromagnetic tensor, and in particular, they have a strong element, matrix element, a transverse matrix element, which is like 4 times stronger than the free electron. And this is good because it means the coupling constant to the resonator will be stronger, and therefore also the radiative rate. So yes, so one interesting aspect is that this is the gyromagnetic tensor that you can find in the literature, but this is of course an average quantity. And now each ion really has its own gyromagnetic tensor that's going to be slightly different from this one due to the local static electric field and the strain that is present at its location. And this is called inhomogeneous broadening, and this is what we're going to see in our experiment. Right, so the experiment just is just that we apply, it's very simple, we apply an excitation microwave pulse to the spin device, and then we just let our counter run over here like 200 milliseconds, so this has like 10 to the 5 cycles, more or less, and we sum all the clicks that we receive during that time, right? And then what we do is we sweep the magnetic field around the resonance condition of the erbium ions. And so you see that we see a very clear peak in the number of counts. This is at high power, so this is the ensemble. This is the many ions in the crystal. And so we can check also that this ensemble peak is really the peak of erbium by verifying what happens when we change the angle of the magnetic field with respect to the c-axis, and we see a nice parabola which corresponds exactly to this ensemble average gyromagnetic tensor. So now the interesting things happen when we reduce the power of the pulse and we integrate for much shorter times. By this way, we actually detect only the ions that are the most strongly coupled to the resonator, so the closest to the resonator, so the ones that will decay as fast as possible. And when we do that, you see that this ensemble line becomes really the sum of many very, very narrow peaks. And each of these peaks is perfectly reproducible, and these are the single ions, in fact. And so this is here a fluorescence curve on top of one of these curves. You see that it decays with a characteristic time of 1.5 milliseconds for this ion. And this is the dark count, so just next to this, if we change the B0 field by maybe 10 microtesla, then there is no fluorescence anymore. And so this is a zoom in a narrow region of B0. And to convince you that these peaks are stable, what we can do is take this narrow region, this is shown here at 0 degree, and change the angle. And by doing that, we see that each of these peaks is actually shifting very nicely with the angle, as it should for the erbium ions, but each ion has a slightly different symmetry axis and a gyromagnetic tensor. The exact values of the gyromagnetic tensor are really a fingerprint of each atom, and it's slightly different from the ensemble average. This is normal. This is really the phenomenon of inhomogeneous broadening, but which is here quite clearly evidenced. So in principle, from this, it could be possible to extract this tensor to really ppm precision or even better if the field was properly calibrated, which is not really the case in our experiment, but that shows the potential of this method. So now we can sit on one peak and study the coherence of these ions. And so this is a Rabi oscillation. We can check that the oscillation frequency is proportional with the pulse amplitude. And we can from this extract one quantity, which is simply the spin-to-click efficiency, right? So what happens if we do one spin flip with a pipe pulse? How many clicks do we get for exactly one spin relaxing? And in our case, this is 0.12. So we get only 12% of the, but it's actually not so bad. This is the total efficiency really of the whole chain. We can also do, because we have a photon counter after all, we should be able to do intensity correlation measurements, and we are. So this is the G2 from this single, so this is, we sit now on a single spin peak, and we measure the correlation intensity function. This is by correcting from the background, because in our case, we have a significant contribution from the dark count, but we can remove it quite simply. And so the corrected G2 is really very clearly below 0.5, showing that this is really coming from a single emitter and a single spin. We can look also at the T2 star. So for T2 star, we find varies a lot from ions to ions, but we've seen values up to 300 microseconds, typical in the 100, 150 microseconds. T2 is much longer. T2 is here 2.5 milliseconds in this ion, but note that this value is actually very close to twice T1. T1 is 1.4 milliseconds. So really there is not so much pure dephasing left. So this is really radiatively dominant. The radiative decoherence is actually really dominant in these systems. And if we add 2 pipe pulses to do a little bit more dynamical decoupling, we reach really exactly twice T1, so we have absolutely no measurable dephasing. Okay, so since last year, this was data from last year, just really to flash you data from this year, a bit newer data. So this is shown on the same scale. The fluorescence, you see the noise is exactly the same, but now we have improved the detection efficiency and also the coupling. We've coupled more strongly the ions, so they relax faster, and you see that we have gained a lot in signal-to-noise ratio. And thanks to that, we can start addressing interesting aspects of these systems, which is the coupling of these spins, these electron spins, to nearby nuclear spins, because this erbium is located in a crystal, and some tungsten atoms have a nuclear spin. And what I want to really flash is very fresh data from a few days, but which I like a lot. And so these data show that we are actually seeing the quantum jumps of one of these tungsten nuclear spins via the electron spin. And so it really demonstrates that we can very clearly use the electron spin to also probe the nuclear spin environment. And so this is something that we're going to study much more in the future. All right, so in conclusion, my time is gone, I'm sorry, but we have this interesting application of superconducting qubits with this microwave single photon detector. Further progress is possible, and applications besides spin detections are really very likely in a number of fields. As regards single spin detection, we think it's really an interesting method because it is universal. It applies to any paramagnetic impurity in principle, non-invasive, of course. That's the beauty of magnetic resonance. And it has a quite large detection volume. So we are very excited to explore the applications of this method to real EPR spectroscopy. And finally, in this experiment, we have tens or even hundreds of very long coherence spins, qubits, that we can also see as qubits, and they are interfaced with the same resonator. They are also coupled to very coherent nuclear spin register. So we are also very interested in exploring the potential of this architecture for quantum computing, for spin-based quantum computing. And so this is my coworkers. I apologize for the extra time. Thank you.
Thank you. Thank you, Patrice. So do we have any questions? Yep.
Hi, so great talk, thanks a lot. Do you know what limits your efficiency? Is it like background thermal radiation or unexpected excitation of the qubit of some sort?
Sorry, I didn't get the question.
Sorry, I was just asking, do you know what limits your efficiency?
Yes. Yes, so the question is about what limits the efficiency. So right now, the first device that I showed had efficiency of 0.43, but in the second, we actually reached like 0.7 after. And we know exactly what limits the efficiency. It's really the qubit T1. So in the first device that I showed, T1 was quite short. It was like 20 microseconds. And now we have, in the latest device, we have 70 microseconds. And it's very simple. It's just that if the photon arrives at the beginning of the cycle, you can absorb it, but then you have time to lose it. So.
Patrice, that's fabulous results. Congratulations. They're really amazing achievements. You showed results on, I think, one material, maybe more than one. What other materials have you tried it on, and are there any constraints on the materials to which this can be applied?
Yes, so this can be applied in principle to any material, so we have a broad spectrum. We are interested in two types of directions. One is really for quantum computing. So for quantum computing, we want, in a sense, the best spins. And actually, calcium tungstate is not bad for that because it has a very low nuclear spin, nuclear magnetic moment density. But it's not great for the Q. So I think we are also interested maybe in titanium oxide, in rutile. We're interested in YSO. Now, another class of another direction will be to apply it to really EPR, so that will be to maybe glassy materials and molecules. So then it's really it will be another type of experiments, and so we don't know what to expect from this, but we're going to also explore that. Yes.
Thank you very much. So in the interest of time, could we thank the speaker again? And next, I'd like to welcome Camryn Undershute from Michigan State University to the stage. Thank you very much, Camryn.
Hi, I'm Camryn Undershute. I'm a grad student at Michigan State University, working with Johannes Paulinen. And today I'm going to be talking about phononic dissipation with superconducting qubits. So this is a superconducting qubit conference. I'm sure we all know and love circuit quantum electrodynamics. In the field of circuit quantum acoustodynamics, we just replace the electromagnetic resonator with an acoustic resonator or a mechanical resonator. And so there's been many different kinds of mechanical resonators that have been developed that we can couple to superconducting qubits. But a really important property of these mechanical resonators is that the speed of sound is much slower than the speed of light. And so that makes these mechanical resonators an attractive component to incorporate into quantum computing applications. Because of this slow speed of light, you can make a resonant device that has the same resonant frequency as its electromagnetic counterpart, but with a much smaller spatial footprint. And so there have been some ideas about how to use these mechanical resonators as a quantum memory. Also historically, they've been used to try to do microwave to optical transduction. But as they are becoming more relevant to quantum computing, it's important that we understand their decoherence properties. Additionally, they're interesting from a fundamental physics perspective. So again, because of that slow speed of light, this enables the exploration of some non-Markovian phenomena. And then additionally, these are all really macroscopic objects. And so it's a further probe of quantum mechanics on a macroscopic scale. Okay, so to start today, I'm going to tell you about a surface acoustic wave resonator, which I think we already heard at this conference, which is exciting. And then I'll tell you about how we can measure and understand the decoherence of our surface acoustic wave resonator, because again, as these resonators are becoming important to quantum computing applications, it's important that we can understand and characterize these decoherence properties. And then finally, I'll talk about how the acoustic resonator imposes decoherence on the superconducting qubit, and how we can actually use this decoherence to do some fun fundamental physics. Okay, So surface acoustic waves are really just the vibrations or elastic waves that travel along all surfaces of materials. But when these travel along a piezoelectric material, there's a co-propagating electric field, and that's what we can take advantage of to design resonance structures that we can couple to superconducting qubits. And so here's a schematic of what one of these surface acoustic wave resonators typically looks like. So the structure in the middle is called the interdigitated transducer, or the IDT, and this is what's responsible for converting electrical excitations into phononic excitations. So when there is a potential difference across the set of finger pairs, this potential will couple to the strain in the material and launch phonons that travel along the surface. And then additionally, we can pattern these acoustic Bragg mirrors onto either side of the interdigitated transducer. And so we can actually use numerical methods to calculate the spectral response of each one of these components. And so here's what those look like for the device that I'll be talking about today. So on the top is the conductance of the IDT, and it has this sink-like structure. And when this has a high conductance, you can kind of think of it that the IDT is doing a good job at converting these electrical excitations into phonons. And then on the bottom, we've calculated the reflectivity of the mirrors. And so in the device I'm talking about today, the mirrors have a very narrow stop band, close to 4.5 gigahertz. But we can take this one step further and calculate the spectral response of the device as a whole. And so it has a very unique, interesting spectra. It's inheriting properties from both the conductance of the IDT and the reflectivity of the mirrors. But this device is designed to host just one resonant mode. And I've had to truncate the y-axis and kind of zoom out on the frequency scale here to show you all the interesting features, but to convince you that there is really just one resonant mode. If we zoom in, it is a nice Lorentzian mode centered close to 4.5 gigahertz. And so to complete this quantum acoustics experiment, or experimental setup, we can fabricate a transmon qubit on a separate chip, and then put them together in this flip chip configuration where both the transmon qubit and the SAW resonator have these large antenna pads patterned onto them, and that facilitates their capacitive coupling. Okay, so next I want to go on to how we can measure and understand the decoherence properties of this surface acoustic wave resonator. So in our spectroscopic data, we can see a large avoided crossing, close in frequency to where we expected to find the SAW resonator. And from this, we can extract a coupling strength of 10 megahertz, so we're in the strong coupling regime. But for these measurements of the SAW's decoherence, I want to tune the qubit in frequency out here towards close to 4.2 gigahertz, which is well into the dispersive regime. And because the SAW resonator and the qubit have a Jaynes-Cummings interaction, in this dispersive regime, the qubit will acquire a dispersive Stark shift that depends on the phononic occupation of the SAW resonator. And so for these measurements, we're going to use this dispersive Stark shift to read out the state of the SAW resonator by measuring the qubit spectrum. And so a first measurement of the SAW's dynamics looks something like this. So this is a ring up, ring down measurement where for times less than 2 microseconds, we are driving the SAW resonator for increasing times, and we can see its state ring up. And then after 2 microseconds, we're turning off the drive and allowing the SAW to evolve freely, at which point we can see its state decay back down to its quantum ground state. And we can fit these to the Markovian master equation and extract a T1 decay rate of close to 3 inverse microseconds. And this is a little bit larger than our numerical methods would have suggested. And so we think that the main decay mechanism here is leakage out of these mirrors. And so those Bragg mirrors I showed you earlier aren't perfectly reflective. And we think that's the main cause of this energy decay. But we think additionally that there is significant conversion from these surface phonons into phonons that live in the bulk of the substrate and that the qubit doesn't really see. Okay, but not only can we measure the energy decay, we can also measure the dephasing of the SAW resonator. We do this with a modified Ramsey sequence where not only do we sweep the time between our 2 Ramsey pulses, but we also sweep the phase of the second Ramsey pulse relative to the first. And so to get an idea of this measurement, when the time between these two pulses is short, you'd expect that it's driven into the largest coherent state when the two pulses are in phase with one another, and then when the two pulses are out of phase with one another, it's driven into a coherent state and then back into its ground state. And our data qualitatively looks like this. So you can see for increasing time, the SAW resonator is driven into a coherent state of the same size regardless of the relative phase of the pulses. So qualitatively, this makes sense. But we can further quantify this by extending the measurement to all times, and then again fitting this to the Markovian master equation, where now not only do we account for single phonon losses like we did earlier with the energy decay measurement, but we also account for dephasing in the system. And so here we get a dephasing rate of close to 0.7 inverse microseconds. And while with the energy decay, we could both quantify and understand, or at least have strong suspicions of the origins of this decoherence, we don't yet understand where this dephasing is coming from in this system. And so currently, we're working to understand where the dephasing is coming from. And then additionally, we're trying to extend this measurement protocol to larger and larger coherent states. OK, so now to switch gears a little bit, I instead want to talk about how the SAW resonator affects the qubits decoherence. So a first probe of this that we can do is measure the qubits T1 decay rate as a function of the qubits frequency. And you see we get this really non-trivial shape to the qubits loss spectrum. And it's been fit kind of suggestively here to this sinc squared function, which actually, if you remember from earlier, was inspired by the shape of the IDT's conductance. Further, you might notice here that we're in a frequency range that's well outside of the stop band of the mirrors. And so these are phonons that are not resonant. These are just lossy phonons. So we can understand this as the SAW, or more specifically really the IDT, mediating the coupling between the qubit and a bath of lossy phonons. And so at this point, you might say, OK, you've made your qubit way lossier. Why is this exciting or interesting? But actually, this shaped loss is one of two ingredients that we can use to engineer coherence in a system when there wouldn't be coherence otherwise. And the second ingredient is a coherent drive. So here's the Hamiltonian for a driven qubit. And we can rotate into the dressed basis by this angle theta, which really just depends on the parameters of the drive. And now you see from our rotated Hamiltonian that the energy splitting between these two dressed eigenstates is just given by the generalized Rabi frequency, which typically is pretty small. So there's no preferential decay between either of these dressed eigenstates. So as you drive your qubit, it just decays to a point in the center of the Bloch sphere. There's no coherence. But if we tune our qubit in frequency to somewhere in its loss spectrum where there's a strong slope in the loss, actually the decay rates of these eigenstates in the dressed frame will not be the same. They will sample different points along this slope. And as a result, we'll get preferential decay from one of these eigenstates into the other, leading to a preservance of coherence. We can understand these dynamics, again, using the Markovian master equation, where the first term accounts for the coherent effects of the drive, and then the next two terms account for the loss rates of either of these dressed eigenstates, and then the last term we need to include to account for global dephasing of the system. Okay, so in general, what our measurement or experimental protocol looks like is that we will drive the qubit for some amount of time with this parameterized drive, and then follow that with state tomography of the qubit. And so here in this tomography, as we increase the drive, you can see that we have the typical Rabi oscillations like you might expect for short times. But then as the amplitude of these Rabi oscillations decays, the qubit state vector does not decay to a point in the center of the Bloch sphere, as you'd expect. Instead, it decays to some superposition state. And so you have this coherence that outlives any of the native coherence times to your system as it's driven. So to quantify this, we can calculate the purity of this state as we drive it, And for a maximally mixed state or a point at the center of the block sphere, we would get a value of 1/2. And you can see that we're far from that. So I think for this measurement, the purity actually decays to a value of close to 0.8. And we will preserve this purity or this coherence for as long as the qubit is driven. And so here you can see that it is stabilizing to a superposition state in the qubit's bare frame. And this corresponds to that rotated or dressed eigenbasis that depends just on the parameters of the drive. So actually, not only can we stabilize this state in particular, but we can choose whichever state we want to stabilize just by changing the parameters of the drive. Okay, so here is the x component of the qubit state vector as we change those parameters of the drive. And you see by varying them, we can go from relatively small to relatively large values of the drive. And again, this is compared to the simulations of that Markovian master equation I showed you earlier. And we get both great qualitative and quantitative agreement. Okay, so because I don't think I have forever, there's a couple other interesting things we've done that I don't think I'd have time to talk about. So this includes measuring the span of states that we can stabilize to. And so we can't stabilize to any qubit state, as you can see here from the bounds on this axis, but we do have quite a bit of freedom and also limitations on the purities we can achieve. And you can find these in this recent publication from our group. But additionally, since then, we've done some more interesting measurements where we can characterize the effective bath temperature that the qubit is coupled to, and we can also even calculate the cooling power of this protocol. Okay, so to conclude, I hope that I've convinced you that we can really tailor the qubit's loss spectrum by its coupling to these lossy phonons, and then we can use this to stabilize almost arbitrary qubit states in this bath engineering protocol. And in the future, we want to design loss profiles to do some more interesting experiments. So because this loss profile really just comes from the geometry of the IDT and the material parameters, we think we have some really fun knobs to turn there. Additionally, all the measurements I've shown today are from the same SAW resonator device. So in one device, we have access both to these lossy modes and this resonant mode. And so we have some ideas about how we can improve upon this bath engineering protocol to use both the resonant mode and these lossy modes. So yeah, with that, I want to say thank you to everyone I work with, and also thank you for your attention.
Thank you very much. Thank you very much, Camryn. That's very exciting. I know exactly why he's going to ask the question. So, Tom, you start. It was really nice results. Excellent.
Thanks very much. That was a great talk. When you drive a system like that coupled to a bath of phonons, you can see population inversion in some cases. Have you seen that in your system?
Yeah, we do see population inversion. So actually, in this region where the x component of the state vector crosses over, we also see population inversion.
Do we have another question? I have a question, but letting everyone else go first. Do you have enough coherence and fidelity and everything to do these more advanced pulsing schemes like CPMG, et cetera, to actually reconstruct the spectral characteristics of the bath?
What we are limited, I think, in that regard right now. So here, the first term in this equation is just loss of the qubit to the environment other than like our phononic bath. And the slope and the amplitude of the second part isn't quite large enough relative to the first term here. So the qubit by itself is already just like a little bit too lossy. So that's something that we're working on.
Yep, sounds good. Do we have any other questions? If not, thank you very much, Camryn.
Thank you.
Let's not swap. You take that one, because we've already swapped it once. So, there we go. Excellent. Excellent. Okay, we now have Matti Silveri from University of Oulu, Finland. Thank you very much.
All right. Let me thank first organizers for the very nice conference, and also I thank the opportunity to give this talk, so I'm very happy to be here. The outline of my talk is first something about transmon arrays, then beyond two-level approximation, and then finally the dynamics. This work is based on 3 works, published works. The main authors are Olli Mansikkamäki, Sami Laine, and Oksana Busel, who are the trio in the middle of this group photo. Transmon is probably at the moment the most important superconducting device, and we have seen many different ways of organizing these transmons in a larger arrays. There are different topologies. There are these heavy hexagons, star topologies, square lattices, linear chains, different ways of coupling them. There are bigger square lattices, smaller star topologies, and then also 3D geometries which allow then more long-range interactions. But let's think about for a while the transmon itself. So transmon is an anharmonic oscillator. So it means that it has many eigenlevels there, typically of the order of 10 in a traditional transmon. In this conference, we have already seen that the 2 lowest levels are the computational states, but then these higher levels have been nowadays used for controlling engineering interactions for readout. But should we think about using more levels of the transmon for actual computations or dynamics? Or, yeah. Let me give an perspective to this through an essay type of article by Bloom, Kahoot, Caves, and Deutsch. It has a nice title, Climbing Mount Scalable, Physical Resource Requirements for Scalable Quantum Computer. And they put it quite nicely, squeezed the idea quite nicely. They said that the primary source for quantum computation is Hilbert space dimension. Hilbert space is a big place, and it's an abstract place. But what do you do when you increase the number of qubits? You increase the Hilbert space. You increase the space where you can do your algorithms, your simulations. And the bigger the Hilbert space, you can say that the more interesting and more fascinating things that can happen there. And how do you can increase the Hilbert space dimension? Well, there are 2 ways. You increase either the physical number of sites, L here, or the site, the local dimension D. If you increase the local dimension D, that would be maybe the hardware efficient way of increasing the dimension. I'm a theorist, and now you may say that, well, it's difficult and challenging in practice, but I would like to now point out the history here on the experimental realizations and studies that the higher excited levels have been characterized, that their decay and coherence properties have been measured. Recently, during the couple of 3 years, we have seen like a gates benchmarking experiments, utilization for these qubit levels for information studies. There has been entangling gates. There has been a realization of even like D to the 4 gates. So I would maybe get from this that it's doable. So now to the dynamics, or inspired by this to the dynamics. So in our work, we are interested in answering the question that if we have now an array of transmons and if I excite one of the transmons to, let's say, third higher excited state, how is the dynamics of that excitation then? We start from a Bose-Hubbard model, which describes the physics of this array. There is the U interaction, which is the unharmonicity. There is a hopping, and then, of course, on-site energy. Let me now solve this by numerics, and that's what I get. So this is solved now by a fixed number of bosons at a fixed length of a chain. All the lines here are many-body eigenlevels. If you see a thick line, it means that there are two lines almost overlapping. And there are now one important thing, or many important things in this plot, but one important thing is that you see these mini-bands. These mini-bands are characterized how the excitations are in this, how is the configuration. For example, the lowest one has all the excitations stacked on top of each other, but the site varies. The next one has all but one excitation stacked, and so on. You go up until you come to the hardcore bosons where you have either 0 or 1 excitation there. And funny thing is that when I say about higher excited state dynamics of transmons, here it is actually the lowest ones, which they are the ground state in this perspective. The mini-band structure here means also that if I now prepare my transmon array into from a configuration that is in one of the mini-bands, it will stay in that mini-band. So there is a conservation law, or approximated conservation law. So, and that's what we are going to utilize here. We want to solve effective dynamics within basically all of these mini-bands analytically. How do we do it? We use high-order degenerate perturbation theory. I won't show you equations, but the basic idea is that we take a certain state manifold, for example, the lowest one, and then we ask that how the stack could move to the next site. It cannot move directly there, but it can go through virtual transitions. There is kind of a paths, and there are different kinds of paths. And by counting these paths and their magnitudes, we can figure out the effective hopping rate from a site to another. Let me now visualize and give some examples of the dynamics that we figure out. So let's focus now on the lowestmost manifold, and there we have these boson stacks. So several excitations on same site, and these behave like quasi-particles, particles that do not disintegrate. So we can define an annihilation operator for them. It just depends where this excitation is created. Then we can write down the effective Hamiltonian, which has two terms, the on-site energy and then the hopping one. The expressions for them are given below, and there are two interesting effects. First of all, the on-site energy has a profile. It's not uniform, despite we start from a uniform distribution in the, like a physical on-site energies, but for these stacks, it's not uniform. Specifically, there is this edges, and the energy difference from the edge to the interior sides, there is a gap. And that's actually bigger than the hopping energy for the stacks. So it means that if you prepare your transmon array, excite the edge transmon of your transmon array to a higher excited state, for example 3, it will stay there. Nothing will happen. It's energetically forbidden. But if you do the excitation in the interior sides, it will start moving, hopping from a side to another, but it won't go to the edges. Let's get deeper. If we add 2 stacks, so then on top of the on-site energy variation and the hopping, we will get an interaction. This is like a particle-particle interaction, but now for the stacks. And what is interesting here and fascinating is that this is non-local, so they feel each other from a distance. This is visualized here in the middle one, where we see that if we put two stacks, one in the edge, it's stuck there, and then one in the middle, and in the middle stack could in principle move left and right, but because there is this non-local interaction from the edge stack, it cannot move there. The hopping is too weak to do that. The only thing is that it can move to the right of that, and that's what we see in the simulation tool. There's also other effects and many and more interesting effects there too. Please see these two papers. Now you are thinking that this is unitary, and how about then dissipation and dephasing? What it will do for all these phenomena? We have studied that. So standard dissipation for transmos gamma, and then dephasing for transmos kappa here. And here we have assumed basically that they are unharmonic oscillators. In practice, we have a stronger dephasing for the higher excited levels that we haven't taken into account here, but we maybe could have. And we have ways of doing that. Let me now describe the dissipation and dephasing phenomena, starting from the strongest one and going to the weakest. First, we have a decoherence coming from dephasing. Now I use a notation where I write the Fock state configuration n1, n2, n to the nl as a vector n. So if you write your Fock state configuration like that, you can quite simply see that the coherence rate between two Fock state configurations can be expressed quite nicely through this expression what is here in the top. So it is a distance in the Cartesian coordinates, like a vector distance between these two Fock state configurations multiplied by the dephasing rate. So that's there. It's happening between any Fock state, between inside the unharmonicity manifolds, between unharmonicity manifolds, and essentially between any Fock states. Then there is a decoherence coming from dissipation, of course. That's just proportional to the number of boson excitations there. Then there is a dissipation, which removes excitations, and you can see these yellow lines telling how states from a certain unharmonicity manifold are mapped then to a next photon number manifold. That's also a rather trivial process. It's removing bosons, excitations there, and the rate is given here. The first non-trivial process is so-called cooling and heating transitions, which come from the combination of dephasing and then hopping interaction. Without dephasing, the protection that protects the state to belong to just a one unharmonicity manifold is quite good, but now when it's combined by dephasing, it leads to transitions from a certain unharmonicity manifold to the next one or the nearest ones. So the first rate here is the rate from the lowest unharmonicity manifold to the next lowest one, and I have here also written down the hardcore boson transition rate. So this is the transition rate out from the hardcore boson manifold to the next below that. And the interesting thing is that it is proportional to n squared. So meaning that the more excitations there are, the more they leak into the next. But this is a weak process because of the J/2. So should be not too worried. How does it look like in our numerical simulations? So here is a plot first on the boson stack hopping. So we take a minimal example that would show the interesting physics here. So we initialize stack at the site 2 and then see how it could go to the stack 3 and does it go to the edges. We choose parameters that we believe that are experimentally realistic. J20, U230, and then T1, T2 as written there. the dashed line is the unitary case, and the solid line is the non-unitary case, taking into account T1 and T2. This example shows an borderline. Here, the dissipation, or actually dephasing, is so strong that it washes away the essentially rapid oscillation between the two sides. There are two reasons for that. The stack hopping depends, the rate depends quadratically or cubically on the J, and then the Fock state difference in this space is large between the two sides, and that gives quite a large dephasing rate for these two stacks. The next example shows an case when you can see this many-body phenomena in there. So here we have three stacks, 2, 1, 3, 2, 2. And here we should see that they don't move, but there is this one excitation hopping from a stack to another. And here the exchange rate is faster, and also the distance in the Fock space is smaller, so then one really sees this unitary dynamics also with these parameters. Now I'd like to point out that if one way, that maybe the easiest way to see this stack hopping would be to increase the J, because if you, let's say, double the J, then the stack hopping rate would go to 8 times what it used to be, and then it's probably visible. So let me conclude. I have explained to you that we have solved the effective dynamics in all of these unharmoniously manifolds. It's both an analytical tool and also a numerical tool. So you don't necessarily need to solve the full numerics, but you can just solve the dynamics within the manifolds. I have shown you these interesting phenomena, for example, stack hopping, edge localization, and stack-stack interaction, and then describe dissipation and dephasing for boson stacks. I would like to also use this chance to advertise that we are hiring. We are postdoc position open until end of this month. I can say that Oulu is a city in middle of Finland, and we are a cool place, maybe very cool. Thank you.
Thank you very much, Matti. So do we have some questions? Yep.
Hi, very interesting talk. I had a question about the symmetry and the heating and cooling rate induced by the hopping. Have you looked at starting from like a formal derivation of the master equation, including in the dressed or the eigenstates of the full lattice? I'm just surprised that there's no dependence on the fact that one transition gains energy and one transition loses energy in the induced heating and cooling, leading to an asymmetry in their rates.
Sorry, I know I didn't fully.
Oh, okay. So I guess if I understood your slides correctly, gamma AB is the same to go up in energy or down in energy. And I just would have, I'm just asking if you've looked at, rather than starting with the Lindblad equation you showed on an earlier slide, and then I'm assuming perturbatively deriving those rates, if you have started from the Hamiltonian for the lattice, worked and then derived the master equation from in that lattice Hamiltonian's eigenbasis, starting with a system bath interaction.
Sorry, maybe I don't know. Yeah, maybe we can.
Yeah, let's talk offline. Yeah,
thanks.
No problem.
Sorry.
So just clarifying, you're talking about doing a Bloch-Redfield type analysis of the spectrum, yeah, because that becomes important when the levels are close together. Yeah. I actually had a slightly different question, which is just one of orders of magnitude. So as the lattice gets longer, the spacing between the relevant levels in the many-body states gets closer. Is that true?
Yes, in the interior.
Interior, yes.
They get like almost the same, but in the edge it stays. It is not dependent on tell its
Yep.
age effect.
Yeah, yeah. So then if you have some dephasing in the system, that sets a width, which kind of is the minimum resolvable spacing between levels you can see.
Yes.
Yeah. So then when doing these kinds of calculations, I'm always interested to know if we make the system longer, that can also be described as a constraint on the dephasing. So the coherence of the transbonds has to get better as you extend. Do you have a feel for whether that's important for the processes that you're talking about?
I would say that the J, like this effective J, which describes the effective hopping of the stack, that should be compared with the dephasing, because I think that tells the coherence properties of these stacks. So I think that's more important.
So it's dominated by the J.
Yeah.
Yep. Okay. Yeah. Good. Thank you. Do you have any other questions? If not, can we thank Matti? Oh, sorry. Oh, yeah. I stopped you earlier, so I better let you go.
Yeah, great. Thanks for the talk. Can you comment a little bit on the equations you had, or the J effective, and maybe the interaction term? Like, it seems like that the effective J goes quickly down, like exponentially down with the number of excitations.
Yeah, that's right. Yeah.
And yeah, and also there's the factorial. So
yes, the factorial comes from the degenerate perturbation theory. So the first splitting is u times n minus 1. The next one is u times n minus 2, and so on. So that's so. So it's not evenly spaced, this one. So when we do this virtual transitions, the denominator holds the energy difference, and that comes from there.
So it seems like that it freezes when you increase n. Can you somehow, is there a way to then to get to larger excitation numbers that still move, like split into smaller groups or something?
Yeah, of course, if you have a very large stack, it moves very, very slowly. That's right. So then it may be better to split it 2 parts. That's right.
Okay, if we could thank the speaker. Next we have Andrei Vrajitoarea, yeah, from Stanford. That was that one.
Right. Okay. I'd like to thank you for the introduction. I'd like to thank the organizers for this wonderful conference and for this opportunity to present our recent work on how we assemble and also probe synthetic quantum matter with microwave photons in our superconducting platform. This is work I did during my postdoc in the Schuster and the Simon labs at the University of Chicago. Okay, great. And the motivation behind these experiments follows this growing interest of understanding strongly correlated materials, both from a fundamental perspective of understanding exotic phenomena in condensed matter physics, and also for harnessing these many body effects for quantum information and for technological applications. And for large system sizes, these models are hard to simulate, so there's a growing effort in engineering quantum systems that are tailored for controlledly simulating the quantum phenomena of interest. So there's been a ton of experimental effort in a lot of different quantum platforms. And today I'll talk about our favorite platform, which is using microwave photons in superconducting circuits. So as a general pedagogical overview, quantum simulation, you have some model Hamiltonian of interest, where you want to study the ground state and some phase transition in the ground states, and also you would like to look at some complicated many-body dynamics. There are typically 2 approaches to do this, both with their advantages and disadvantages. You have the digital approach using a universal quantum computer, where the idea is that you can trauterize your Hamiltonian to to discretize your unitary evolution into a set of local single and 2-qubit gates. And the idea is that for this process to be efficient, you need a lot of gates, and you need the gates to have small errors. But this does promise a universal simulator. You can kind of encode any type of model as long as you have error correction built in. And then there's the second approach, which is using an analog simulator where you encode your model directly in the lab, and you can efficiently simulate dynamics in real time. And the caveat is that it's not as universal as a quantum computer approach. As long as you can implement your model, then you can use this type of simulation where you can efficiently encode the problem, you can run it in real time, and you're less prone to errors as you are in the digital approach. And this is the type of approach that I like to use in our simulators. And this is actually where the circuit QED community has developed a lot of the critical pieces for building synthetic quantum materials and also for doing quantum simulation in general with microwave photons. And in the interest of time, I'll just highlight the ingredients we use in our recent work, which is where we want to develop a quantum platform that's based on implementing a one-dimensional Bose-Hubbard model for microwave photons, where we want to pattern an artificial lattice where photons, or particles in this case, can coherently tunnel between lattice sites, and this is how the photons inherit an effective mass similar to electrons in a crystal. And you have these particles will experience strong local interactions. And this competition between the kinetic energy and strong particle collisions will give rise to strongly correlated phases, where in this case you have a Mott insulator or a superfluid in this one-dimensional case. And to understand how we synthesize this material in superconducting circuits, let's start from the basic building block, which is, in this case, a single lattice site. And since we're dealing with bosons, it's natural to use microwave oscillators to represent the single lattice site. So the simplest thing you can make in the lab, as we all know, is you make an LC circuit. But since you need interactions, the next easiest thing you can do is replace your inductor with a Josephson junction to make our favorite transmon qubit, where in this case, the Josephson nonlinearity that gives rise to a particle confined in the cosine potential, this type of nonlinearity gives you this anharmonic energy spacing, where we use this anharmonicity to basically introduce this effective energy potential, to have an effective energy interaction cost to add an additional particle into your system. And the way we couple our lattice sites is quite easy, as we all know. We just couple them through a capacitor, and this allows the photons to coherently tunnel between different lattice sites. And as we add these ingredients together, this gives us our one-dimensional Bose-Hubbard model, where the transmons shown here as the blue crosses, there are lattice sites. The quantum particles, in this case, are microwave photons. They're tunneling across the lattice sites, and they experience strong local interactions. For our system, the tunneling rate J and the on-site interaction U, it is fixed. The only thing that we have in situ control of is the resonant frequencies of the transmons. And this allows us to tune the disorder in situ in real time, as I'll show you later. Okay, so this is our whole device. I already described the type binding chain of transmons. So this is where the science happens. As I mentioned, each transmon has a squid. We can inductively couple each transmon to a flux bias line. This allows us to tune the resonance frequencies and basically play around with the lattice potential in real time. And then we can perform on-site spectroscopy or on-site microscopy of the lattice occupation, coherence, and also look at correlations by coupling each transmon to its own readout resonator and a Purcell filter. And just to kind of give you a broad overview of the platform and what are the parameters, compared to our coherence times, our lifetimes, we have that our tunneling times are about 3 orders of magnitude faster, so we're in this quantum coherent regime. And on top of that, we have our interaction strengths are another order of magnitude bigger than that. So we're in the many-body regime, where for the experts in the audience, we're dealing with hardcore bosons confined in one dimension. Okay, so this is a growing field where there are many, many research groups around the world who are studying Hubbard models with superconducting circuits. And as you put all of these ingredients together to engineer your target Hamiltonian, that's actually the first is just the beginning of the journey, because what is equally important and actually quite challenging is to prepare entangled states, target entangled states in a large quantum system. And even if you can do it, how can you tell you prepared an entangled state? How can you characterize it? How can you benchmark it? And these many-body problems, they present kind of a central challenge in quantum information science, not just in many-body physics, but also in quantum information and quantum metrology. And this has been the major theme of our research at UChicago, where we've been working on developing various new state preparation techniques and new types of probes. And in this talk, I'll just briefly highlight our efforts in using the sorter to prepare strongly correlated photon fluids, and also how we can use our site resolve control to also prepare the lattice in a coherent superposition of being both in a solid and in a fluid phase, and how this connects to preparing a highly entangled Noon state. And finally, I'll briefly show you how we can also entangle the state preparation task, entangle it with the characterization task using an ancilla qubit in order to extract many-body information using Ramsey interferometry. Okay, so to prepare our quantum fluid, we essentially leverage our control of lattice disorder, as shown in this diagram, as I mentioned before. We start in a strongly disordered limit, where the lattice sites are tuned so far apart that tunneling is prohibited. So this allows us to, so in this configuration, any type of many-body state in this case just corresponds to a bit strain. It just corresponds to photons localized in each lattice site. That's very easy to prepare. We just apply pi pulses. Right? And then what we do is we remove the disorder by tuning the lattice sites into resonance, by tuning the transbonds into resonance. And we want to do that slowly in order to be adiabatic. And the reason why we want to be adiabatic is we want to stay in this instantaneous eigenstate, and this allows us to melt these initially localized particles into a strongly correlated fluid via tunneling-induced quantum fluctuations. And then at the end of our protocol, we do site resolve measurements of the population, of the coherence, and also of site resolve correlations. Okay, so to benchmark quickly this, because I'm running out of time, so let's see what the single particle case looks like. Here I'm showing you what the eigenstates are as a function of disorder. When you're strongly disordered, that just means you have a photon in one lattice site. And as you go to near zero disorder, it just corresponds to a single photon particle in the box eigenstate. And adiabaticity just ensures that there's this one-to-one connection between where you initially put your photon, where you initially localize it, and which quasi-momentum state it corresponds to. And here I'm showing you the data as you go along this trajectory where you initially put a photon, in this case, into qubit number 5, because that's the highest state. And then you slowly remove disorder, and you can see that this photon delocalizes into one of the sine kx, the lowest order sine kx quasi-momentum state. And the way you can tell if you're adiabatic, the approach that we do is quite easy. So we have our same melting protocol where we remove the disorder, and then we reverse the process. Let's reintroduce disorder in a symmetric fashion in order to relocalize information. And that's a much easier approach to do rather than doing tomography near the degeneracy limit, since that state can be highly entangled. And in order to probe adiabaticity, whether you're adiabatic, the question is very simple. Can I reverse this process and recover the same initial state you started in during this protocol? In this case, since you're relocalizing information into each lattice site, that just corresponds to measuring the populations of all the qubits and see how it correlates with what you started with. And we do this procedure over 4 orders of magnitude in our ramp rate. And I won't go much into detail, but basically we can find the optimal ramp rate at which we can recover our initial populations. We can do this for more than just a single particle, and that's how we calibrate our multi-particle melting protocols. So here I'm showing you free particle melting, where the many-body spectrum can be quite complicated as a function of disorder. And here I'm showing you in real time what the density profile looks like as you sweep disorder. Initially, free photons are localized at the corresponding sites. They would correspond to this eigenstate. And then as you remove disorder, you can see that these free particles will eventually delocalize into a strongly correlated fluid. And we do this experiment of both for 2, 3, and 4 particles, where you can see the density profile, how it evolves as a function of disorder. And here at the bottom, I'm showing the density profiles as a function of the number of photons you delocalize. And one thing you can notice is that the shape of the density profile looks very different and it scales with the number of photons you put in. And obviously, interactions play a big role, because if you had no interactions, then you would expect all the density profiles to look the same. But if you add in strong interactions, and you take into account the many-body wave function, indeed you recover with theory, analytical theory, you recover what the density profile looks like. And this shows you that indeed the interactions are shaping the fluid density profiles. And in order for us to probe ordering of how the photons kind of delocalize and experience strong interactions, then we need to look at correlations and measures of entanglement. So I'm just going to briefly show you what we do. We measure particle correlations using this pair correlation function, G2, but this is now in space, where you measure the probability of detecting simultaneously 2 photons spaced away by lattice spacing x. We do this for various filling fractions, and we can see that our model fits a Tonks-Girardot gas model, where you have a spatial anti-bunching, where as you have more photons, they'll have less space, so you have a smaller spatial anti-bunching region. And also, you can collapse all of your data by rescaling the position axis, and you can see that you get oscillating correlations. For the experts in the audience, these are just Friedel oscillations, and these shows you how the photons, as they're experiencing strong interactions in one dimension, confining their quantum fluctuations in one dimension, they're now behaving as non-interacting fermions. Okay, so I showed you how quantum computing platforms can be efficiently used in our system to assemble quantum matter. So let me end by showing you how, in the spirit of this session and this conference, how we can leverage dynamics in our Hubbard model to implement a many-body gate for generating a highly entangled state in our quantum computer. And we also can explore ways in which we can probe entanglement with a single ancilla qubit. The idea, I'm going to go through it very fast. I'm sorry about that. But we start in a staggered configuration where we have some sites on the left and symmetrically some sites on the right. The sites on the left, they're going to be at a higher frequency, and then we're going to adiabatically sweep the system where we go to a reverse staggered configurations where now the sites on the right are at a higher frequency. And we're going to use the fact that we have a middle ancilla qubit where we detune it by the anharmonicity. So the F state is now in resonance with the other qubits, the E states of the qubits. And you can see that, okay, let's say if we put photons on the left, but the middle ancilla qubit is not excited, then the F state is not accessible. You can't tunnel and delocalize these particles, so what you get is a solid. It's a Mott insulator. But now if your ancilla is excited, then you can delocalize the free particles on the left, and you can have a strongly correlated fluid. So we use side resolve control and conditional state preparation, in this case, to prepare a conditional many-body swap. But then one interesting thing is that if this ancilla qubit is now in a superposition of being ground or excited, then at degeneracy now you have a superposition of it, the lattice being both in a solid and in a fluid phase. And then as you go to the reverse staggered configuration, this corresponds to you preparing a new state. And I'm going to go through it fast, but we'll also use this ancilla to perform Ramsey interferometry, where we apply this entanglement operation. We wait some time to accrue some phase. Then we reverse the entanglement operation in order to disentangle the ancilla and relocalize the phase information on the ancilla to measure the fringe frequency. If the ancilla was not entangled with the other qubits, then you just get some bare Ramsey frequency. But as we perform this entanglement operation, you can see much faster fringe frequencies. Now, how fast? Well, the frequency difference basically tells you the information where the energy difference, the frequency gives you the energy difference between the two configurations you're entangling. And the fact that they're oscillating means that you're probing coherence. You really do have a coherent superposition. You have coherence in this entanglement. And you can say, OK, well, just because you measure something that's fast doesn't necessarily mean that it's like a really smoking gun signature of entanglement. So one thing that we do also is we see how this many-body Ramsey peak varies as a function of intentional offset. Let's say we move the left-hand side lower, the right-hand side upper by delta, and we see that the many-body Ramsey peak, it shifts by the Heisenberg limit. Basically, you can see that the sensitivity of this entanglement scales with the system size. OK, so with that, I've hopefully convinced you that circuits, our platform, is like an appealing platform for quantum simulation. It offers unique preparation and characterization protocols compared to traditional AMO experiments. I'm looking forward to expanding this many-body toolset and also applying these techniques for more complicated many-body models with even more exotic properties than the standard Bose-Hubbard model. Since I'm running out of time, let me just thank my group, and thank you for your attention. I'm happy to take any questions now or during the break. Thanks.
Thank you very much, Andrei. Do we have one quick question? Yeah. Oh, many one quick questions up there. Sorry, Andrei.
Hello. Thank you very much for your talk. I would like to ask, how does adiabaticity work for highly excited states? Because the level spacing for many-body states is quite low. So you need to do your quench really slowly, but on the other side, then you're more subjected to the dephasing and decay.
Yes, so that's a very good question. I think it comes from the fact, like, your question is probably like, what happens if I make the chain longer, right? J is constant, many body energy levels are getting closer, you have to be slower, but you have a fixed coherent budget. So one thing that I skipped over was that we used, in a previous study, we used dissipation we used engineered energy-dependent loss to stabilize the photonic Mott insulator, where we had a gap. And we're thinking of ways in which we can use the same trick, where let's say we don't do perfect adiabatic preparation. Let's say we can prepare our fluid state, but also we get some higher energy excited states, many body states. Those are actually phonons. We actually know how we can deterministically prepare those phonons, and we're thinking of ways in which we can use dissipation to cool down the phonons to our many body ground state, despite the fact that this fluid is a compressible phase. So we're thinking of ways in which we can do the normal adiabatic approach, but also use dissipation to cool down the system a bit more to remove the entropy in an irreversible way.
Thank you.
Hi, thank you very much for this very nice talk. I have a very quick question. So you mentioned about the superfluid, fluid, solid state, and maybe also gas state. What's your criteria? Is that a photon number density that distinguishes the different phase, or your correlation?
Yeah, it's a mix of both. So we measured the G2 correlation. You're right, we more have like a Tonks-Girardot gas because our interactions are local. If we had a bit of a longer range interaction, then this would be more of a superfluid. We also do entanglement measures, so we know that as the particles, the photons delocalize, they also mediate entanglements between qubits. So this is how we can kind of say for sure that, fine, this is not a superfluid, but this is definitely a strongly correlated fluid.
Thank you very much, Andrei. There are a few people still wanted to ask some questions, so I highly recommend they chase you down during coffee break. Now I'm hoping we have our last speaker for the session. Yes, good, excellent. So we have Zenghui from Tsinghua University, who will be talking about experimental preparation of generalized and multi-pair cat states. Thank you very much.
Good morning, everyone. Thanks for the chair and thanks for the organizers to give me the chance to speak today in this fantastic conference. And I'm a PhD student do experimental work with superconducting qubits in Lu Mingduan's group in Tsinghua University. And I'm very glad that I have this opportunity to share with you the work I have been doing on experimental preparation of generalized and multi-party cat states for itinerant microwave photons. So let's start with a brief introduction of the background of this topic. In 1935, Erwin Schrödinger devised the famous thought experiment as shown in this figure. A cat is entangled with a radioactive particle, and they are placed together with a mechanism such that the decay of the particle will trigger the release of the poison and kill the cat. The possible decay of the particle brings the cat into a peculiar mixture of being dead and alive. Well, in practical experiment, the classical object is usually emulated by the microscopically distinct state, for example, the coherent state with the same amplitude but opposite phases. And the atom can be natural atom or artificial atom, such as the superconducting qubits or other two-level systems. Over the decades, K-states have been prepared in various physical systems. For example, firstly using the vibrational state of a trapped ion in 1996 by Weinland's group, and the cat was produced with state-dependent dipole optical forces. And then the K-state of stationary photon modes were created in superconducting cavities, coupled with Rydberg atoms by Delaglis of Harash's group, and coupled with the superconducting qubit by Velastaki of Shokhov's group. And after that, the K-state of propagating photon modes were created in circuit QED system by Pfaff of Shokhov's group, and in cavity QED system by Hacker of Ramp's group. Their work has inspired us. Their work has inspired us a lot for the follow-up work, and there are also a lot more nice work about K-state, and I have only listed some of them here. In our work, we demonstrate a versatile and highly scalable approach to prepare the generalized and multi-party K-states for itinerant microwave photons in circuit QED system. Our work is based on the cavity-assisted interaction between the flying photons and the local matter qubit, which was first proposed by Duan and Kimball for photonic quantum computing. And then a specific proposal to prepare the flying photonic K-state was later raised by Wang and Duan with the Duan-Kimball scheme. In microwave regime, such control Z gate between the photons and the qubit was first implemented respectively by Bessie of Wolff's group and Kono of Nakamura's group in 2018 to perform a single-shot quantum non-demolition detection for itinerant microwave photons. And in Bessie's work, they have also prepared a nice K-state. Our experimental setup is similar with Kono's scheme as shown in this figure. The system is composed of a transmon qubit, shown with the red part, which can provide nonlinearity to the system, and a three-dimensional superconducting resonator, shown with the blue part, which can interact with the flying photons. The implementation of the control Z gate is based on the reflection of the resonator and the dispersive coupling induced by the qubit. And the upper two figures show the three-dimensional superconducting resonator used in our experiment. And the qubit chip is placed inside the cavity and coupled with the resonator. The three-dimensional resonator is designed with two outcoupling ports, but in this experiment, only port 1 is used as a reflection port for the propagating photon mode, and port 2 is blocked. The outcoupling strength of this resonator with the propagating photon mode can be precisely tuned by changing the length of the coupling pin inserted into the three-dimensional cavity. And for this resonator, the reflection spectrum can, for this resonator, the reflection spectrum can be described by this equation, where kappa 1 is the outcoupling strength of the resonator with the propagating photon modes, and kappa T is the total energy loss rate, which contains kappa 1 and the internal loss of the resonator. And omega is the frequency of the input signal, and omega 0 is the frequency of the cavity. Due to the dispersive coupling with the qubit, we can see the frequency of the resonator will be shifted by a positive or negative chi according to the qubit states. And thus, if we set the frequency of the input signal at the bare frequency of the resonator, the reflected signal would have the same amplitude but different phases. We can see in this formula, when the kappa 1 is set to 2 times the dispersive shift chi, the denominator equals 0, and the phase would be pi over 2 or minus pi over 2, according to the qubit state, raising a pi phase shift of the reflected signals. And in this situation, the input coherence state alpha after reflection would be alpha r or minus alpha r condition on the qubit state, which means the control Z gate between the propagating photon and the qubit. And the right figure shows the reflection spectrum of our three-dimensional resonator, and the dashed line indicates the bare frequency of the resonator, also the frequency of the input signal. And on its right, this figure shows the phase difference of the reflected signals, and we can see it reaches pi at the target frequency. So with this control Z gate, we can realize full control of the superposition of the coherent states. The sequence of the scheme is shown in this figure. Firstly, we prepare the qubit at a superposition state 0 plus 1 and send the coherent state microwave photon pulse into the system. After response to the cavity, the reflected photon states are entangled with the qubit state as 0 alpha plus 1 minus alpha. And then qubit rotation R theta psi is applied on the qubit, which rotates the qubit with angle psi along theta axis. Subsequently, a projective measurement is applied on the qubit state, and the reflected photon state are also gathered by the homodie setup and sorted by the measurement result of the qubit state. The photonic state is reconstructed by the calculated moment with the maximum likelihood methods, which was first proposed by Eichler of Worf's group. And so we can have the qubit state dependent photon state as the following equations. So by changing the angle psi and theta, we can change the weight and the phase of the superposition of coherent state, and we can get the desired superposition forms. That is the generalized cat state. So this figure shows the experimental result of experimental Wigner function of our prepared generalized cat state. The left figure shows the results when scanning psi from 0 to pi over 2, while keeping theta at 0. We can see the reflected photon state gradually evolve from a coherent state to the even or odd cat state, and the fidelities are labeled in each figure. The right figure shows the results when varying theta from 0 to pi while keeping psi at 0. And we can see the transformation between the even and the odd cat state, and the phase evolution can be clearly observed from the interference fringes. All these states are prepared with the amplitude alpha equals 1.07, which can be controlled by using different input coherent states. So we also prepared the even and odd cat state with different amplitudes. But the larger cat states suffer more from the cavity loss and results in lower fidelity. As a result, the largest cat state prepared in our experiment is alpha equals 1.31, and the fidelity is reduced to about 0.7 for the even cat state and 0.62 for the odd cat state. The next part is the preparation of the multi-party cat states. The scheme is similar with the generalized cat state, where a chain of coherent state photon pulses is sent to the system rather than the one photon pulse. And it should be emphasized that obtaining well-defined multi-party cat state requires carefully determined photon pulse length and the time interval between the pulses to fit the bandwidth of the cavity and to ensure the photonic mode can be well distinguished in the time domain. Thus, the multi-party cat state can be obtained as the following equations. Of course, some additional qubit rotation can be inserted in the photon pulse train to realize more superposition and entanglement structures. And for the single party and the bi-party cat state, we use a calculated moment to reconstruct the density matrices. But for the tri-party and the quadruparty cat state, it costs too much time to reconstruct the density matrices. So we change to the method based on the measured histogram, which was also proposed by Eichler's work. And we use a CG-APG maximum likelihood estimation algorithm proposed by this work to reconstruct the density matrices, and the two methods give very similar results for the single party and the bi-party cat states, which verify the validity of these two reconstruction methods. In this slide, we show the experimental result of the multiparticle cascade with the amplitude alpha equals 0.72. And the density matrices of the multiparticle cascade in the fork basis is very large and sparse, so we plot them in the cat basis for clarity, and there are only small population outside not shown. In the figure, the plus and minus states represent the single mode even and odd cascade, and the transparent boxes indicate the corresponding ideal state. In figure A and B, we show the density matrices of the biparticle cascades, even and odd biparticle density matrices. And in figure C and D, we show the density matrices for the even tripartite cascade and the quadripartite cascade. The corresponding fidelity are listed above each figure. And in figure E and F, we show another kind of bipartite cascade with a qubit pi pulse inserted in the two photon pulses. We can see the additional qubit pi pulse refocuses some of the qubit defacing and leads to an effectively longer qubit defacing time and results in a higher fidelity for the bipartite cascades. From the experimental results, we find that most odd cascades suffer more. They have a larger error than the even cascade. This is due to the error mainly comes from the cavity loss and the qubit decay and defacing. Both of the error will lead the prepared state to a mixed state of the coherent state alpha and minus alpha. Well, for the even cascade, they have a higher fidelity with a mixed state than the odd cascade. So the fidelity between the mixed state and the ideal, even, and odd multipartite cascade can be described by the following equations and plotted as a function of the photonic mode number in this figure. And we can see the difference term scales exponentially with the cat size. With the cat size, and which indicates that the infidelity difference will reduce with the larger cat size. To confirm the existence of quantum entanglement, we calculate the localizable entanglement of our prepared state as a function of the mode number. Our localizable entanglement is calculated by projecting the photonic mode apart from the first and the last one to the eigenstate of operator X, and calculating the negativities of the reduced bipartite density matrices. In this figure, the scattered plot gives the experimental result of our prepared state, and the solid line is the theoretical result of corresponding ideal state, and the dotted line is a theoretical result considering the possible cavity loss and the qubit decoherence and defacing. The positive localizable entanglement verifies the existence of quantum entanglement, while an optimized lower bound can be acquired by choosing a more suitable projection basis. Besides the multipartite cascade, we have also prepared the Schrödinger's cascade, which describes the hybrid entanglement between the qubit and the multipartite photonic states. The corresponding density matrices are plotted in these two figures. The photonic part of the density matrices are also plotted in cat basis for convenience. And compared with the corresponding ideal states, we measure the fidelity of 0.59 for the qubit and a single party cat system, and a fidelity of 0.58 for qubit and a biparty cat system. And to witness the quantum entanglement of this hybrid entanglement system, we also calculate the localizable entanglement from the reconstructed density matrices, and it gives about 0.2 for the qubit and a single party cat system, and 0.13 for the qubit and a biparty cat system. Then, according to the error budget, the cascade generation protocol can be further improved by surprising the cavity loss and the qubit qubit lifetime. Here, eta is a parameter quantifying the cavity loss, and for lossless cavity, eta equals 1. In our sample, eta equals about 0.86, and the qubit lifetime T1 is 20 microsecond, T2 is 7 microsecond. Here we take alpha equals 1 for theoretical simulation with another condition same as the experimental setup. And the red figure shows the expected fidelity with the photonic mode number when eta equals 0.99 with the blue lines and 0.999 with the red lines. And the red figure shows the results when the qubit lifetime T1 and T2 both raise up to 15 microseconds. And with both the cavity loss and the qubit lifetime improved, we estimate that the multi-party cascade can be prepared with alpha equals 2 with 9 photonic mode, or alpha equals 0.5. There is a typo. Alpha equals 0.5 with 15 photonic mode. They can be prepared with a fidelity above 90%. So in summary, we demonstrate a versatile and highly scalable approach to create the generalized and multi-party cascades for itinerant microwave photons. And with our sample, we have prepared the generalized cascade with different phase, weight, and amplitude, and the multi-party cascade with a photonic mode number up to 4. And we have performed full quantum state tomography of the propagating photon mode and calculate the localizable entanglement of the prepared state and verifies the existence of quantum entanglement. According to our error analysis, the current results are mainly limited by the cavity loss and the qubit lifetime, finite qubit lifetime. So it can be further improved by surprising the cavity loss and improving the qubit lifetime. With that, I'd like to thank my team and thank you for your attention. I would be happy to take any question you may have. Thank you.
Thank you very much. So do we have any questions for our final speaker? What do you think if you want to improve the fidelity beyond 0.9, be higher than 0.9, what are you going to do?
I think the best way is to improve your sample parameters about the cavity loss or the qubit lifetime, because we use quite modest parameters. It's not so long. So you can get a better results, better fidelity with for example, qubit lifetime about 1 millisecond. That's that.
Thank you very much. Do we have any other questions? Oh yes, one at the back.
Hello, thanks very much for this very nice talk. And I think it's very interesting that in your bottom right corner, your experiment setup, you are measuring the reflection. My concern is the following, because according to the input-output theory, your output field will always be the input field plus square root of kappa times your intracavity field. And I'm thinking that maybe it's very tricky to remove this reflected input field. Is that a problem, or it's not a matter at all in your experiment?
Remove of the reflected signal?
Yeah, because what I'm understanding is that depending on your qubit state, and your input photon will be absorbed or reflected. But according to the input-output theory, even if you think it's absorbed, but if you are at a single photon level, your output field will always have this proportion of this input field. I'm thinking that maybe you need to use some trick to remove it, or it's not a problem at all in your experiment.
Sorry, you mean maybe the measurement-induced defacing for the qubit? Maybe I'm not getting it so clear.
Okay, maybe we can discuss later.
Oh, thank you.
With that, oh, sorry, Mikko.
Nice results, thanks. I just have to ask this. You have 300 nanoseconds time between the pulses, and as I far as I understood, like each pulse is like each of your alphas. You have alpha to the power of something, so depending on how many pulses, the power increases, right?
Yeah.
So you have 300 nanoseconds between the pulses, and then you're saying that you make this alpha to the power of 4 states, but there is quite a long time between the first and the last pulse. Yeah. So do you have, like, how, is actually the first pulse already destroyed before the last pulse is made? Because you measure it, right? Then you destroy the coherence in your measurement setup.
Actually, I think we can have some additional qubit rotation, for example, like the echo pulses to refocus some of the qubit defacing or about the just the qubit defacing and lead to an effectively longer coherence time for this.
Well, I was simply referring to the fact that, you know, the speed of light, I mean, in 300 nanoseconds, isn't that like 30 meters plus that you will need cable so that your pulse 1 is not at your amplifier before your pulse 2 is made?
So, sorry, I'm maybe not get so clear.
Okay, we can talk later.
Sorry.
Okay, thank you. Can we thank Zenghui and all of the speakers for the session? And now it is coffee time, and coffee is downstairs, and could you all please be back here by 11:10? Thank you very much.
That's the clicker, essentially. So, it's already on. If you start speaking, they will.
Welcome back. My name is Mikio Nakahara from IQM Finland, and it's my honor to chair this, the second session in the morning. The first speaker is Professor Professor Andris Ambainis from University of Latvia. The title of his talk is Quantum Algorithms for General Search Strategies. Please start.
Thanks. So looking at the possible applications for quantum computers, one big and extremely important class of applications is simulating physics. And then there are also problems in classical computing and data processing for which we would like to have faster solutions. And that is a focus of my research. I'm a computer scientist by origin, and what I'm interested in is how one could use quantum computers for the problems that classical computer science is solving, many of which amount to some form of data processing, whether it's machine learning or scheduling. And among the possible tools that we have found for solving problems in classical computer science, one of the big ones is search. So the Grover's algorithm allows to search with a quadratic quantum speedup. We can search n possibilities in time order square root of n. And there are several possible issues with that. It's not clear if quadratic speedup is big enough to make a difference for quantum computers. And then another issue is that a simple use of Grover's search speeds up the most naive classical search algorithm. And there is much more in classical search than the naive algorithm. So the comparison should be quantum search versus the best classical search algorithm that has been invented. And for example, one can think of traveling salesman problem in which we have to find the best routes through n cities. There are n factorial candidate routes, so using Grover would give you an algorithm that would solve the problem in times square root of n factorial. But at the same time, traveling salesman problem is something on which classical computer scientists have worked for 50 years, and even though it still requires exponential time, there is an exponential time algorithm that is faster than square root of n factorial. So one of the things on which I, as a computer scientist, have been working is how to combine quantum search with the best possible classical search strategies and to get the best of both worlds, to get quantum algorithms that are better than any classical search algorithm. And there is a number of results in this direction. There are specific classical search algorithms that one can speed up, and there are a whole class of general search methods that quantum can speed up, from amplitude amplification to quantum divide and conquer. So a quantum search can go far beyond simple application of Grover's algorithm. And those algorithms typically still provide only a quadratic speedup, but they solve a much wider range of problems. So in search, there is a number of problems for which one can get some degree of quantum speedup. And today I will talk about two of those results, two quantum speedups for general search strategies, which are quantum speedups for search with backtracking and search by quantum walk. So let me first talk about quantum search by backtracking. Backtracking is a search algorithm that is widely used in classical computing to solve constraint satisfaction problem. It's one of those core computational tasks that run in the background and solve many practical problems. It's something that is usually not noticed, but it solves a lot of problems. It solves problems in scheduling, it solves problems in natural language processing. A lot of things work by first converting the problem into a form where one can use search by backtracking and then applying a standard search algorithm and fine-tuning it for the specific problem as much as one can. So for example, in natural language processing, one can convert the problem that one wants to solve into a system of logic constraints and then solve this system of logic constraints by backtracking. And so what backtracking means is that, let's say that we have a search problem that we want to solve. And we build up a sequence of partial solutions, with each partial solution having more and more information. And the goal is to go through more and more detailed partial solutions to a full solution to a problem. So we start with a solution where we know nothing, and then we try add something to this empty solution. And then if at some point we get stuck, that is, we discover that we cannot extend this current solution any further, we go one step back and try something else. And if that fails, we go 2 steps back. So this is sort of a smart way of covering a large possibility space. And the classical art is choosing the right direction and finding out where we can cut off some branches of the search tree. And to make this more concrete, one thing that one can solve are integer programs that are often used for scheduling. So integer program is essentially a system of linear inequalities with variables being 0 or 1, where 0 and 1 corresponds to decisions that we might make, which would be, for example, sending an airplane on this route or not sending it. So we can describe an airplane scheduling problem through linear equations, and then it becomes a problem about solving a system of linear equations with variables that are 0 and 1. So in this case, backtracking would solve the problem by making guesses about values of variables. So we would start with a state where we don't have any guesses about anything, and then we would make guesses about variables one by one. And if at some point we discover that our guesses have led us to a situation which is not going to lead to a solution, we step back and try another value for one of variables which we have set. So this is an example of search by backtracking. And quantumly, we can solve it by a quantum walk, which is a process where we have a walker walking on the search space. So this search space would exist in a memory of a quantum computer. It would be a search space with basis states corresponding to vertices in this search tree, and then we would have some superposition of these over these states stored in the memory of a quantum computer, and we would perform a quantum walk on this search space by applying local transformations. So local transformation means that we look at an element of this. For each element of superposition, we are examining the neighboring vertices, and we are performing some transformation that only sends amplitudes to those vertices. So for each element of superposition, we only need to calculate information about its neighbors. And then this quantum walk would start at a vertex corresponding to root of this tree. That is vertex where we have no information about the solution of problem that we want to solve. And then if we set this walk properly, it would lead us to the solution that we want to find. This quantum walk would settle in a state which is a superposition over the path from the root to the solution state. And then we can find the solution by measuring this state. And the result is that there is an almost quadratic speedup over conventional search by backtracking. So search by backtracking is the best and commonly used strategy for quite a few problems. And then whatever it gives, we get a quadratic speedup over that. And then one can do various other things with these search trees. For example, if we want to estimate the size of this tree that this algorithm is going to search, there's also a quantum algorithm for that. And another reason why this algorithm is interesting is that in its essence, it's a relatively small memory quantum algorithm. If the size of this tree is n, then one can store the state of a quantum algorithm into just log n qubits. So there are particular cases of this algorithm that are simple enough to implement. It doesn't need much memory. The depth of computation is a bit larger, but there are still particular cases that might be implementable. For example, if we took a tree with depths 3 and 7 vertices, then one step of this quantum walk is implementable with 5 C0 and 2 Toffoli gates, which is not awfully large. So I think that this might be an interesting test case that would test quantum devices in a bit different mode from ones in which they are typically tested. Okay, so now let me quickly say a few words about the other algorithm that I was going to describe. So this is search by quantum walk, and it solves a general situation that one can call proximity search, in which we have a search space, and we want to search this search space for an object with a certain property, which is represented by this vertex in orange. And this search space has a structure that makes it easier to check vertices in certain order. So if we have checked vertex 4, it might be easier to check vertices 2 and 6 because we can reuse some of the information that we had from checking vertex 4. So classically, one strategy for searching a search space like this would be randomly walking on it according to this structure. And then quantumly, there is an interesting tool that has been developed 5 years ago, which is called quantum fast forwarding, which says that if you have a classical Markov chain that satisfies certain properties, then you can quadratically fast forward this Markov chain. So in a certain, a little bit unorthodox sense, you can perform t steps of a random walk into square root of t quantum steps. And then we can make use of this tool and speed up any classical search strategy that searches by performing a random walk. So if classical random walk finds a state with a certain property in time t, then we can do it by quantum algorithm almost quadratically faster, subject to certain technical constraints, which I'm not going to describe. And the algorithm is, again, we perform a quantum walk on this search space. So both results that I'm describing in this talk are based on quantum walks. It's a bit different quantum walk here, but it's also a walk in which we perform local transformations, but only send amplitude between neighboring vertices in this structure that we are searching. And in this case, we also need to perform a transformation in which the number of steps of quantum walk that we are performing is encoded into another quantum state. This is what is needed for this quantum fast forwarding. So the simplest particular case would be that we perform either 0, 1, or 2 steps of quantum walk, depending on on a 2-qubit register. Okay, so to summarize, we can combine quantum algorithms with smarter classical search strategies and get quantum algorithms that beat both the best classical algorithm and naive quantum search. And in this talk, I sketched how this happens for 2 general search strategies. There are more examples of that. And for both of those that I described, there might be some small instances that can be turned into a test that can be performed on a near-term quantum devices. Okay, that's all. Thanks.
Well, the session is open for questions and comments.
So the speedups that you've shown for both of these cases and all the other cases were always quadratic. I want to ask if it is because kind of in the core, in the end, they are all based on the Grover's algorithm or kind of on the same principles?
Yes, that is the case. So the underlying principles are similar to Grover's algorithm. So the speedups that we get are at most quadratic.
Any more questions?
Yes. Back in the corner. Yes, hi, thank you for this talk. I'm really cool to see that actually here at SQA. My question here is like one of the things classically that one might do in this type of backtracking algorithms is to backtrack many different paths in parallel using more like, parallel computers. Is that something you might be able to do using the quantum box as well? Or are you forced to do all of that now serially because you have a superposition that you're working in?
Okay, so can you repeat it? I didn't hear it very well.
Is it possible to to parallelize this type of quantum walk over maybe multiple quantum computers in the same way that you would be able to parallelize the different backtracking on classical computers?
Okay, I have not thought of this, but it sounds plausible. Okay, it sounds plausible that it would parallelize both classically and quantumly by splitting the problem, and then you would get a similar relation between parallel classical and parallel quantum.
Okay, thank you.
So I have a question here on the last bit. You're saying that small instances could be a test for near-term devices. What would you be interested in testing on these near-term devices? So we saw that these circuits, but what would they reveal?
Well, yeah, I would be interested in testing how well these circuits work and like how much of steps of quantum walk one is able to implement, and then also I guess how to implement it optimally. I think there is some natural implementation what comes to my mind when I just think of it on the paper without implementing. So is that the best way, or is there something else that will come up?
Okay, let's thank the speaker. The next talk is by Shao-Hen Chiew. The title of his talk is Scalable Quantum Computation of Highly Excited Eigenstates with Spectral Transforms. Please.
How does the laser work? Okay. Firstly, I would like to thank the organizers for allowing me to speak here. It's a really great conference. My name is Shao-Hen, and I'm currently working with Entropica Labs at Singapore, where we design software for error correction. But in the next 15 minutes, I'll be presenting about a work that I did at the Center of Quantum Technologies in NUS, Singapore, with my supervisor, Professor Quek. And the title is Scalable Quantum Computation of Highly Excited Eigenstates with Spectral Transforms. To keep this talk as self-contained as possible, I will spend the first 2 sections of my talk explaining what the quantum linear systems problem is and what spectral transformations are. And using ideas that we built from these 2 parts, I will explain. I will describe an algorithm that we introduced to solve for highly excited eigenstates of physical and chemical Hamiltonians using these ideas introduced in the first 2 sections. So I begin by describing what the quantum linear systems problem is. We are given a vector B of dimension n and a square matrix A of dimension n times n. And in addition, we also have some assumptions on the matrix, like the fact that it's Hermitian, invertible with eigenvalues that lies between 0 and 1, with sparsity S and condition number kappa. So the sparsity here refers to the maximum number of non-zero elements in the rows of the matrix, and the condition number refers to the ratio between the maximum eigenvalue and the minimum eigenvalue of the matrix. Okay, so the procedure that I'll be describing works for arbitrary matrices, but I would like to mention that we are particularly interested in matrices that arise from physical and chemical contexts. And so, for example, k-local Hamiltonians that can be written as a linear combination of Pauli terms that act non-trivially on at most k qubits. So these are called k-local Hamiltonians. And I use the notation small n to indicate the number of qubits, so that the matrix dimension big N scales exponentially, is equal to the power of the number of qubits. So the linear systems problem asks for the vector x that solves the linear equation ax equals to b up to some error epsilon. And it is known that the best general classical solver in this case is the conjugate gradient algorithm with a runtime as follows, where the big O notation there indicates the asymptotic upper bound of the runtime. In this case, we see that it scales linearly with the matrix dimension. So going back to our example of physical Hamiltonians, if our problem, going back to that example, this dimension scales exponentially with system sizes typically. So there's a small problem here. On the other hand, the quantum linear systems problem asks for, instead of a vector, a quantum state x that encodes the solution of the linear equation ax equals to b. And more concretely, it means that we want a quantum state with amplitudes that correspond exactly to the elements of the vector x that satisfies ax equals to b. And for this, in this case, the HHL algorithm is the first algorithm that was proposed to solve this problem with runtime that looks like this. And interestingly, you will notice that instead of scaling linearly with n, it now scales as the log of n. So that's an exponential improvement in matrix dimension, and that's pretty nice. So going into a bit more detail on this, on this algorithm, so I display the circuit here, but the details are not important. The only thing that I want to mention here is that we have to have some way to access the input matrix A. And in this algorithm, it is done through the quantum phase estimation part. And in particular, we call Hamiltonian simulation to access the matrix. And indeed, the log n scaling for this, for the HHL algorithm comes from the time it takes to perform Hamiltonian simulation. So again, to summarize, Hamiltonian simulation dominates the runtime of the HHL algorithm. Now, a lot of improvements have been made. The HHL is the first algorithm, after all, using a lot of new ideas. And qualitatively, I just wanted to show that the runtime in the scaling in the matrix dimension is preserved, and the scaling in the inverse error can be improved by an exponential factor. So now it becomes log of the inverse error. And I'll also note that all of these algorithms require high-depth circuits. So we will need error-corrected, fault-tolerant quantum computers to actually execute them. With that said, luckily, there are actually implementations of, there are actually studies of algorithms that can be executed on near-term devices. So I won't be able to go into the details too much. But if you're familiar with variational quantum algorithms, it works in kind of a similar way. We have a kind of cost function that we can minimize. And by finding the cost function by finding the quantum state that minimizes this cost function, we essentially are able to solve the quantum linear systems problem. And I hope you will believe me when I say that this cost function, when we minimize it, it solves the problem, and that it can be computed on near-term devices. I'll refer you to some of the works below if you're interested. And so being a variational algorithm is a bit difficult to study the runtime of this thing. So numerics are required. And fortunately, the authors actually do some numerical simulations to show that it actually scales quite similarly with HHL, which is pretty nice. So now, having talked about the complexity of the classical and the quantum solvers, it might be tempting to just jump to the conclusion and say that there's some kind of exponential speed-up associated with the HHL algorithm or any other quantum linear system problem solver. But actually, the answer is not so straightforward. We actually have to go a bit into the details. And actually, I'm just parroting what Scott Aronson said in this paper over here. So suppose that we're given some kind of generic linear algebraic application where we want to solve the linear system. So in fact, there are several problems. So firstly, the input vector B needs to be mapped to the amplitudes of the quantum state D. And this, in the absence of any structure, any knowledge about the vector B, is actually, it might take as many operations as there are entries. So this is quite bad. And secondly, we must be able to access the matrix A efficiently. And in the case of HHL, this was done through Hamiltonian simulation, right? And in the complexity just now, it was assumed to be efficient at log n. But there might be cases where the matrix just cannot be simulated efficiently. Thirdly, it also must be well-conditioned with a kappa that does not grow too much. And finally, the output quantum state X needs to be mapped back to a classical vector. And again, this is, at worst, it might take as many steps as there are entries in general if we do something like full quantum state tomography. So having discussed that, let's move on to a slightly different topic about spectral transformations. So it solves a different problem. It is a technique that is known classically to solve for highly excited eigenstates. So just to describe the problem, the task is the following. We are given a Hamiltonian H, and we wish to prepare a representation of one of its eigenstates. It could be the ground state, could be the excited state, could be something that is highly excited. And this is nice because once that is done, we can subsequently extract physical information from it. We can do some tomography that is cheap. We can measure observables from it to learn about some global statistical properties. And it's generally quite useful across different fields of science. Given the importance of this procedure, these algorithms, there are a lot that is known on how to solve them. So there are classical algorithms that are known, there are quantum algorithms that are known. And these are predominantly for ground state problems. And to adapt this thing for our highly excited eigenstates, and I put an emphasis on highly here because we're really not, I'm considering a case where we don't just look for eigenstates that are close to the extrema of the spectrum. We really talk about eigenstates that are located in the bulk of the spectrum. And for these, we can try to adapt ground state methods, and some of them work. But generally, the problem becomes difficult when we increase the system size. So that brings me to a description of spectral transforms. The idea is actually quite simple. What we want to do is to design some kind of transformation such that the target excited state that we want to find of the original Hamiltonian H becomes the ground state of the transform Hamiltonian. And I hope you agree that by solving the ground state problem of the transform Hamiltonian, we are able to find the ground state of, the excited state of the original Hamiltonian. So we are interested in a particular kind of transformation called the shift-invert transformation. So literally, we have a shift. We have a shift in energy in sigma, and then we invert the whole thing, where sigma is a number that lies between the maximum and minimum eigenvalues. So the thing about this transformation is that we can see that the eigenstates of H are also eigenstates of the transformed Hamiltonian. And furthermore, that their energies are transformed in a similar manner. This is kind of simple to see. We start from the eigenvalue equation of the shifted Hamiltonian, and we get to the final equation, which just shows that the claim is true. So that's nice. But what we actually care about is a second feature, which is that the eigenstates of H with energies closest to the shift now become extremal eigenstates of the transformed Hamiltonian. And actually, it's a bit simpler to show as a diagram. So what I'm doing here is that I'm just kind of peppering the eigenstates of the original Hamiltonian on the real number line. And suppose that I've kind of selected a shift there somewhere in the middle. What the transformation does is that it transforms the eigenvalues of the original Hamiltonian according to this reciprocal function. And you can see, for example, if you track the green eigenstate I've marked, it is originally located in the middle, but now it becomes the extrema of the ground state of the transformed Hamiltonian. So this is how the thing generally works. So there are many different ways to choose these transformations, such as perhaps you didn't want to do an inversion, you could just square the thing and it kind of works. But there are some properties of the shift-invert transformation that makes it particularly nice. And I'll just go through it very briefly. For example, you see that close to the asymptote, eigenstates are actually very heavily repelled from its neighbors. So that's a nice feature. It allows us to distinguish between the energies of these neighboring eigenstates. And secondly, there are even better cases where the entire neighbor is shifted to the other end of the spectrum. So those are nice properties that we want. And indeed, this intuition is confirmed if you do simulations. Shift inversion is one of the ways to produce state-of-the-art results when you perform these kind of simulations. OK, so our core question is really the following. Can quantum algorithms somehow help to do something better? Which brings me to the description of the algorithm. So what you want to do, what the algorithm does, is that it prepares a ground state of the shift-inverted Hamiltonian on a quantum computer. And if, again, you're familiar with variational quantum algorithms, it kind of works the same way. We want to minimize the cost function. And the cost function here happens to be the shift-inverted Hamiltonian. And so by variationally, so what we want to do is find a quantum state that minimizes this cost function. And that allows us to find the ground state of this shift-inverted Hamiltonian, which, based on what we've discussed on the spectral transformations, correspond to the excited state of the original Hamiltonian. So now, it seems that the non-trivial part of this algorithm lies in how to compute the expectation values. And indeed, this is kind of like the trick that we use in this algorithm. So how do we compute that value in brackets? So again, I remind you that suppose that we have some linear system AX equals to B. What does it mean to solve this? It means that we're able to prepare the quantum state X. And after we prepare it, we can measure some kind of observable M, right? Now, consider the case where we select the input matrix and the observable to be the same, the shifted Hamiltonian. By the way, the tilt indicates the shifted Hamiltonian. And what we find is the following series of equalities. I'm basically just applying the condition for the linear system to the left-hand side. And the thing to notice is that we can now compute the left-hand side by just evaluating expectation values on the output of the QLSP. And that's really nice. So again, to repeat, to compute the expectation values of inverses, we essentially have to solve a quantum linear systems problem and measure on it. So even more interestingly, I think, is in the way that we have used this algorithm. Let's go back to the fine prints that we were discussing just now about the problems of the QLSP solver. So in fact, the way that we use it is rather natural in the following ways. The quantum state B here, actually, because we want it to ultimately be representing eigenstates of Hamiltonians, there's no mapping that is needed. And we can even exploit advancements in Ansat's design to prepare this quantum state in a very motivated manner. And secondly, H, being the Hamiltonian of physical systems, is generally sparse and simulatable. So, so the log n scaling is preserved. And finally, we only ever ask for statistical quantities from the output of the QLSP. So there's no need to convert to a full vector. So these are nice reasons that make this application a kind of natural way to use the quantum linear systems problem solver. So how much time do I have? Okay, thanks. So sorry, but I don't think I have enough time to go through the details. But yeah, if you work out the complexity of this procedure, in particular the complexity of the computation of the expectation value, you'll find that there is a new dependence here, where delta is the kind of the energy gap between the target eigenstate and its neighbors, and this is quite intuitive and I guess. I also wanted to show some applications of the thing. So for example, here what I'm doing is that I'm trying to recover a particular potential energy surface for a highly excited eigenstate. And we compare it with the shift squaring, and we find that generally it's quite nice. But this assumes that the energy gap is known. But there are also situations where we don't have this knowledge, and it turns out that we can make use of some information about the Hamiltonian that is not explicitly the energies, and still do something interesting with it. So yeah, I'll have to end my presentation here, but we have an archive paper out, and we'll be it's kind of outdated, but we'll be updating it soon. But I'll be really happy to take any emails, any questions. Thank you.
Thank you very much. One or two short questions.
So I have a question about when you had the final scaling, there was the dependence on the delta, which was the difference between how close are the eigenvalues. And I wanted to ask, like, is that where the sigma comes into play? Because how does that matter, right? Because if you put the sigma really, really close to the eigenvalue, it will be really, really deep.
Yeah, exactly. That's kind of where this originates from.
Okay, thank you.
Thank you for your talk. In one of the last slides, you showed that you apply your method to MBL systems. But for MBL, the eigenvalues, which are neighbors, I'm
sorry. Could you repeat the last sentence?
You showed that you applied your method to MBL systems, Heisenberg chain.
Yes.
And for MBL, it is known that neighboring eigenvalues, they can be quite different in terms of local operators. How about the accuracy, sensitivity to, say, your shift parameter and so on, and condition number?
Thanks. Yeah, thanks for the question. Yes, indeed, for MBL, there's a particular structure to the eigenstates that has been exploited in like classical methods. Here, actually, I'm just doing a simple simulation for illustrative purposes. But one point that I wanted to mention was that the first question was asking about the scaling of the spectral gap, right? And that typically vanishes exponentially quick with increasing system size. And this is what you see in the middle of the spectrum, where all of the eigenstate energies become concentrated. And it becomes very difficult for the shift-inverted cost function to distinguish between eigenstates. And that's where knowledge about the system that you're working with comes in. For example, he mentioned that nearby eigenstates of the MBL systems have very differing physical structures, spatial properties. So yeah, that's one way that one can exploit structures that is known to overcome the vanishing of the spectral gap. I'm sorry if I didn't understand your question directly, but we can discuss about it.
Yeah, sure. Thank you.
Thanks. So when you shift and invert a Hamiltonian, like this is mathematically just the energy-dependent Green's function, isn't it?
Yes.
So does that mean this same approach applies equally to all sorts of scattering and transport problems? Like when I calculate a transport problem, I'm literally calculating G of E, which is what you're doing.
I see. Yeah, unfortunately, I don't know too much about those, but
yeah, I mean that's exciting, is what I'm saying.
Thanks.
Cheers.
Just short question. Hello. So if I remember correctly, the QLSP requires a Hadamard test to calculate it, which requires a lot of controlled operations. I wanted to ask if you've done the experiments, and given the current hardware, do you see limitations in the accuracy?
Yes, this question is about the near-term implementation of the quantum linear systems problem solver. Yeah, in this slide. Yeah, indeed. This cost function can be written as a sum of overlap terms where we use Hadamard test to evaluate. I did some numerical simulations of it, not extensively though. It works, but I can't say that much about the accuracy. But I think it would be really interesting to kind of implement this on real quantum computers, and especially when the cost of this thing actually is pretty good for many-body spin systems.
Well, I'm sure there are many questions, but please continue discussion after at lunchtime. So we are slightly behind the schedule. So let's move to the next talk by. The next talk is by Nick Blunt from Riverlane. The title of his talk is Statistical Phase Estimation and Error Mitigation on a Superconducting Quantum Processor, please.
Okay, so firstly, thank you to the organizers for giving me the chance to speak at this really nice conference. So today I'll be speaking about a project that we worked on at Riverlane, and the goal of this project was to perform some chemistry calculations on Rigetti's quantum processors and to investigate the impact of error mitigation for this task. And the particular algorithm that we decided to focus on is a type of quantum phase estimation, or QPE. So QPE is widely expected to be an important algorithm for doing chemistry on future quantum computers, but it's very challenging to perform on current devices, mainly because the circuit depths involved tend to be very high. So in this work, we focused on a variant of QPE which has been developed within the last few years, which is referred to as statistical phase estimation, and is expected to have some benefits for nearer-term devices. So in this talk, I'll try to give an introduction to this technique and talk about some of the tricks involved in getting this to work on current superconducting devices. So the task that we're interested in trying to solve is to find the ground state energy and perhaps a few low-lying excited states of some given molecule. And the way that statistical QPE does this is actually quite straightforward. And so this is the circuit that we're interested in. It's just some Hadamard test where we want to perform this controlled time evolution operator. So in the time evolution, we have H, which is the Hamiltonian for the molecule that we're interested in. And it's very well known that by setting V to the identity, or S dagger, so that you're measuring in the X or the Y basis, this allows us on average to estimate the real and the imaginary parts of this GK quantity, which is the expectation value of the time evolution operator with respect to your initial state psi. And here tau is just some rescaling factor for the Hamiltonian, and K will be chosen from the integers. So why is this interesting? Well, if you just expand the initial state in the eigenbasis of the Hamiltonian, then it's fairly straightforward to see that this GK vector can be written as a sum of signals, a sum of oscillating signals, and the frequencies of those oscillations is given by the eigenvalues of the Hamiltonian, lambda I. So in theory, if you can extract those frequencies, then you know the eigenvalues of the Hamiltonian, right? So just to make this super clear, if psi were an exact eigenstate, then of course you'd only have a single term in this summation and just a single frequency. In the more realistic case, where psi is just an approximate eigenstate, then we're going to have a sum of terms with different frequencies. Okay. But in either case, if you have enough data and the noise is well enough controlled, then it should be possible to extract these frequencies and therefore the energies. Right? And the simplest way to do this would just be a usual Fourier transform, but it turns out that this doesn't lead to the most efficient method. And so various authors have been developing these statistical phase estimation techniques to try and make this as efficient as possible. And the approach that we've focused on is the one developed first by Lin and Tong, and then later improved by Wong, Bertet, and Campbell. So here you define some CDF, or cumulative distribution function. And so this C of x is defined as the sum of all probability amplitudes for eigenstates whose energy is less than x. So to try and make that clearer, I've included this example. So here we have some molecule with just 3 energy eigenstates, and so the exact energy eigenvalues are given by the dashed vertical lines that you can read off the x-axis. And the CDF plotted in blue, as you'd expect, it starts at 0 and finishes at 1, but it has these jump discontinuities, and the location of these jumps is exactly the energy eigenvalues. So the idea is if you can construct this function, then you can just read off the energies from this CDF, from the locations of these jumps. So then how do we go about constructing this from the GK values that I was just describing? So firstly, we need to redefine this a little bit to be 2-pi periodic. The reason for this is just that we're going to write this as a Fourier series. So this just allows us to use a discrete Fourier series. So now C of x is rewritten as a convolution between some probability distribution and theta. So theta is just the Heaviside step function. And so one of the key points in this derivation is that we need to write a Fourier approximation to theta. Right? So we need to write some Fourier approximation f of x to this Heaviside step function. And so driving this is actually probably the most kind of tricky part of driving this method. Fortunately for us, this has already been done in the 2 references that are given here. And we've followed the approach of reference 2 here by Wong, Bertet, and Campbell. And so once you have this Fourier approximation for theta, you just plug it into the expression for C of x, and after a few lines of algebra, we get our final result. So here, C tilde, the tilde is just reminding us that this is an approximate CDF because we've used this truncated Fourier series. It's just the sum of all k values from -n to +n, and at each value of k, we need to calculate we need to estimate each GK via the Hadamard test that I was describing. And then you just plug those values into this expression. And again, you should be able to read off the energies from the CDF. And I'll show some examples of that in the results later. And so a key point here is that actually these Fourier coefficients fk decay superpolynomially, and this is the main reason that this is more efficient than just taking a Fourier transform. And so this method is like a little bit abstract to derive, but ultimately this is just some way of extracting the frequencies from these GK values. Okay, but this unfortunately is still very challenging to perform on current devices because in the Hadamard test we need to do this controlled time evolution. Even for very simple molecules, you know, with a handful of orbitals, the Hamiltonian might have hundreds of Pauli terms, and so this quickly becomes unmanageable. So to make this possible, we've used a variational compilation technique. There was a talk yesterday about a very similar idea, and so here we define some parametric circuit. This consists of alternating 1-qubit and 2-qubit layers. So the 2-qubit gate layers are just CZ gates. The 1-qubit gate layers have these U3 operations. So a U3 rotation is just an arbitrary 1-qubit rotation, which is parameterized by 3 Euler angles, and it has this standard decomposition into Rx and Rz gates. So each U3 gate has 3 parameters, and we just optimize those by minimizing this loss function, right? So this is trying to match the action of this parametric circuit to the desired unitary. And so a nice thing about this is that it automatically compiles everything down to a linear qubit topology and automatically to native gates for Rigetti's architecture, for example. So it is important to point out that the way we're doing this currently has an exponential pre-processing step because you need to be able to construct this unitary classically to be able to perform this optimization. There are some techniques, in particular reference 2 here, suggests ways to make this more scalable by using tensor network methods, for example. So in the future, this could be made more scalable, but for now, this is just a necessary approach to make the circuit depth manageable. Okay, and we are also interested in combining this technique with error mitigation. And the main technique that we've focused on is very well known. It's zero noise extrapolation, or ZNE. So the basic idea here is that we're going to parameterize our expectation value in terms of some error rate, lambda. And by varying the error rate in the circuit, we hope to be able to extrapolate down to a lower error rate, ideally to 0 error. And so we define our original circuit as having error rate 1. And then we increase the noise in the circuit through the simplest possible method, so-called identity insertion, where we choose a subset of gates in the circuit, and we just repeat them using this formula. And we choose to only fold the 2-qubit gates, the CZ gates, just because obviously these tend to have the highest error rates. And so this circuit would be error rate 1, this circuit would be error rate 3, and so on. And so we don't try to play games with picking subsets of CZ gates to fold. We always fold all of the layers in practice. And we also apply randomized compiling, which is a technique that allows you to convert coherent circuit errors into stochastic Pauli errors. So again, the bulk of our circuits have these alternating U3 and CZ gate layers. So what you do in this method is you would insert random Pauli gates before each CZ layer, and because CZ gates are, of course, Cliffords, you can always apply the cancelling Paulis afterwards. And then you need to repeat this procedure to average it over lots of different instances of random Paulis. And in doing so, you will convert the coherent error channel into a Pauli error channel. And so a nice thing about combining this with statistical phase estimation is in statistical QPE, we have to perform a very large number of circuits anyway. So we have to perform a circuit for every K value, but also for each K value, we need to perform many circuits to control the statistical errors, right? So actually, these 12s can be incorporated into the method essentially for free, right? And I'll argue at the end of this talk that actually this technique works very well, and actually it's quite important in making statistical phase estimation kind of tolerant to noise. Okay, so the results that I'm going to show on the next 2 slides are from Rigetti's Aspen M3 QPU. They all run through Rigetti's cloud service. And so firstly, we're looking at a H3 minus molecule in a minimal basis set. So this example has 4 electrons in 3 orbitals, and the Hamiltonian can be represented by just 4 qubits. So including the ancilla, this is 5 qubits for each circuit that we're performing. And firstly, we're looking at the GK vector, which I spoke about on the first slide, and looking at both the real and the imaginary parts of this vector. And the results in blue, red, and green are with ZNE error rates 1, 3, and 5. And you can see that the results oscillate as you expect, and as you increase the error rate, you get an exponential decay in signal. But then the results in purple are the ZNE extrapolated results, and they do, it seems to do quite a nice job of correcting this error in practice. And then we take these GK values and we plug them into this formula that I motivated earlier, and this gives you the CDF, the cumulative distribution function. And so again, the dashed vertical lines here are the exact energies that you'd read off the x-axis, and you can see that all of these CDFs have their jumps in the correct places, which would allow you to read off the energies of this system, or at least some of the energies. And again, as expected, increasing the error rate causes a loss in signal, but this seems to be quite nicely corrected by ZNE. And then as a second example, we're looking at a molecule which is relevant for a pharmaceutical application. Here, just taking a chemically relevant active space of just 4 electrons in 4 orbitals as a first approximation. So here, the Hamiltonian consists of 6 qubits. And so again, including the ancilla, each Hadamard test has 7 qubits in total. And again, looking at this GK vector, or the time evolution vector, the results are roughly similar to what we saw on the previous slide. So we get some oscillating signal, but now there's only a single frequency present here, which is suggesting that the initial state for our Hadamard tests is already a very good approximation to the ground state of this system, in this case, because it happens to be single reference. And so indeed, when you plug these into the formula for C of x, you see that there's only a single jump present, and this very nicely matches up with the ground state energy for the system. And so again, the fact that there's only a single jump here is telling us that this is a single reference problem. And again, ZNE seems to do a nice job at correcting the loss of signal that we get in this case. And so I think these results are encouraging, and they seem to suggest that if we can properly tailor the noise and apply appropriate error mitigation techniques, then this method can be made quite robust to noise. But I just wanted to finish with a result that I find quite interesting, which is that this seems to hold even in the case of using a technique like trotterization. So in the previous results, we've used this circuit compilation technique to reduce circuit depth. However, for a truly scalable method in the future, we would need to use a technique where the circuit depth increases at least linearly with K, such as trotterization. So here we're looking at the simplest diatomic molecule, H2, in a minimal basis set. Because this example is so simple, the Hamiltonian can be represented by just a single qubit, and the Hamiltonian has 2 terms, just x plus z. So a single trotter step looks just like this. It contains just 4 controlled C gates. And the results here are just simulated, so we're applying some large coherent error, a type of ZZ error, to each CZ gate in the circuit. And what you get out are these results in blue. And you can see that there's this very large discrepancy from the location of this jump to the exact results, which is this dashed vertical line. But then when you go and try and mitigate coherent errors using randomized compiling, we find that this is entirely removed, this error. Right? And so we're once again able to accurately get the ground state energy for this system. And so I think this result is potentially very useful. I can give a kind of rough theoretical argument for why this might be the case. So this is the GK vector expression that I showed on the first slide. And if we had just depolarizing noise, then we'd expect the circuit depth to, we'd expect the signal to decay exponentially with circuit depth. And so now this GK picks up this e to the minus gamma k factor. But remember, all we're trying to do is to extract the frequencies from this object. So including an exponential decay shouldn't affect those frequencies at all. It just makes them more challenging to extract. Right? So this is kind of roughly arguing that if we can tailor our noise properly, then there are reasons to think that this should remain somewhat robust to noise in practice. And so I think that's an interesting result that we'd like to investigate further by looking at some more challenging examples. Okay, so just to finish by thanking my colleagues at Riverlane, so especially Laura Tsauner. So Laura is a quantum scientist, mostly working on quantum error correction, but she also did a lot of really great work on this project. And then also various collaborators at Rigetti, who have worked with us very closely on this project, and always really great to work with. So that's it. Thank you for listening.
Thank you very much. Now the session is open for questions, comments.
Hi. On one of your slides, you mentioned it was a pharma example. What makes it special for of interest to pharma? Pharma. It said pharma at the title, so. Are you looking at other molecules beyond this right now?
Yeah, so I can't remember all the details. Sorry. Yeah, so I can't remember all the particular details of that molecule, but yes, it was an example that was motivated by some pharmaceutical application. We have people on our team who think about these things, but obviously we have to reduce it to a much smaller active space to make it kind of feasible to look at on current devices. And so we use some chemical embedding method to just try and take the smallest chemically relevant active space for the reaction that we're interested in. Yeah, I'm not sure if that answers your question, but
Hi, thanks for the interesting results. I wanted to ask, when you mentioned when you were computing the cumulative distribution function, there was a prefactor that you said vanishes super polynomially, right? When you say super polynomially, is it polynomial or is it exponential? And did you determine this like in theory or is it numerical?
Yeah, so the results of those Fourier coefficients are derived from the two papers that I mentioned. So it's definitely, I'm not sure if it's technically exponential, but it's definitely faster than polynomial decay. Yeah, I think it might not be exponential, but yeah, this is, as I mentioned, quite important to the efficiency of the method. So one point that I didn't go into in the talk, just for the sake of time, is that actually we don't calculate every terminus summation, but rather we just use importance sampling to just sample from this summation, because the values of fk, you know, at k is equal to 100 can be orders of magnitude lower than k is equal to 1. So it makes more sense to spend more time sampling at low k. All right.
Thanks a lot.
The last question.
So there was some variational ansatz for the unitary evolution operator, but how it works in practice. So you don't know the exact evolution operator. So what is the idea? How you could even do that in practice? So I didn't get it.
Yeah, so in practice, because these are very small systems, we can just construct the desired unitary exactly. So it is just a brute force approach to compile the circuit. So we have the controlled time evolution operator, so we know the exact Hamiltonian, and so we can construct this classically. And so it's just minimizing the loss function that I showed to try and match.
So it will not work for the larger Hamiltonians, yeah?
For larger systems?
Yes.
Yeah, at the moment we're just considering these smaller examples, and this is a necessary approach. I agree it's not the best, but so as I mentioned, there are some techniques like in reference to that I mentioned on that slide, which attempt to do this optimization with more efficient approaches like tensor network methods. We haven't considered that here. This was just a first attempt to reduce the circuit depth. Another possibility would be you could use this technique to compile sub-circuits within the full circuit. So that's one way to get around like a growing number of qubits. But yeah, for this work, it was just like I say, a necessary approach to reduce the circuit depth.
Thanks.
Let's thank the speaker again. Let's move to the last talk of the morning session by Francois Jamet from IQM. The title of his talk is Anderson Impurity Solver, Integrating Tensor Network Methods with Quantum Computing.
Hi, I'm Francois Jamet. Okay, first I would like to thank the organizer to give me the opportunity to talk today. And today I'm currently working at IQM, but I will present a work that I did when I was at the National Physical Laboratory in the UK. And today I want to present the Anderson impurity solver that we have developed, which integrate tensor network methods and quantum computing. So I'm aware that you may not be super familiar with Anderson impurity model and material simulation in general, so I want to spend a bit of time to present what do we mean by first principle calculation, in particular for strongly correlated material. So I will start with like a well-known material, strontium vanadate. It's a perovskite transition metal oxide. So that's already like a metal that we know which is supposed to be strongly correlated. And how we do that is, well, the first thing we do is we apply a perturbative method to this material, and what we obtain is the distribution of state with respect to the reciprocal space. And what you see here is that the band, which is in red, is relatively localized in energy over the reciprocal space. So something which is flat in the reciprocal space, if you do a Fourier transform, that will be relatively localized. And because this band is also partially filled, that means that we will have a lot of quantum fluctuation on these bands. So we have the two ingredients of strong correlation. Like because the band is relatively localized, the Coulomb interaction will be important, and that means that perturbative method will not work to describe this material. So we need to go beyond that, and one method which has been used for a while in the community is the dynamical mean field theory, which map this band to what we call an Anderson impurity problem. Composed of, here we have 3 impurities because we have 3 bands, and these impurities are coupled to a bath. So that's the kind of system which is one of the most challenging to solve for today, real material calculation, and that's exactly the type of system we want to solve on a quantum computer. Like that's really, if we want to be able to have a predictive theory for material simulation, and in particular strongly correlated material, we really need to go beyond the method that we have now to solve the Anderson impurity problem. And it's because and the part which is on the left, well, that is working well with a conventional computer. We don't really need a quantum computer to treat this part, and we want to combine the two, indeed, to get a predictive method. So in the rest of my talk, I will present a method to solve this Anderson impurity problem. Okay, so first, just to describe a bit the structure of the Anderson impurity problem. So as I said, we start with an impurity, so that's a set of sites which are correlated. So we have some Coulomb interaction on it, and that's linked with some hybridization Hamiltonian to a free electron bath which represent the rest of the system. And in principle, this bath is infinite, but here we will deal with a quantum computer with a finite number of qubits in general. So we will need to discretize the bath, or this sum will be finite. And what do I mean by solving the Anderson impurity problem? Usually we mean that not only getting the ground state, but the green function. So not only just the ground state energy, but also the dynamics of the system. So the green function is this physical object which we start with the ground state, and then we apply an excitation to this ground state. So we add an electron, and then we let the system evolve. And if you are a bit familiar with quantum simulation on quantum computer, well, the time evolution is a relatively natural operation to do, because we know, at least conceptually, how to do it. We do a Suzuki-Trotter expansion, and then we can just let we know the quantum circuit to do the time evolution. So there is a good chance that the green function could be computed relatively easily on a quantum computer. So the first step is to get the green function, and then we will talk about how we do the dynamics. Well, to prepare the ground state, okay, there were supposed to be some animation, but anyway, to prepare the ground state, here we can do it with tensor network. So we can do it classically. And in general, I would say that if something could be done classically, probably we shouldn't bother too much to do it on a quantum computer. So the way it works is we use a sparse representation of the wave function. So the wave function, in principle, is encoded in this tensor. And in general, we can always decompose this tensor as a product of matrices. The only problem is that the size of these matrices scale exponentially. But we can put a bound dimension to these matrices, and then change the values of these matrices to minimize the ground state energy. And that works if the entanglement of the system is not too high, or the entanglement of the ground state in particular. These sort of techniques exist as well to do the time evolution, but it appears for the complex Anderson impurity model, doing the time evolution with tensor network is relatively difficult. So where we can see that we have maybe a scope for finding some sort of quantum advantage, because we can do the ground state with tensor network and then use our quantum computer to do the time evolution. So now, okay. So as I said, we have the ground state with a matrix product state, but that's not the end of the story. We still need to load it to the quantum computer to do the time evolution. So what we do is we do some sort of variational algorithm. We start with an NZAT, which is our quantum circuit, and we want this NZAT to represent our wave function. So we want to maximize the fidelity between our NZAT and the tensor network. So here, all this operation is done on a classical computer because that's just tensor network calculation. And the way we do the minimization is we iteratively minimize each 2-qubit gates here, and we keep repeating until the fidelities reach the value that we want. So that's like the DMRG-ish technique, let's say. So that's not something we have developed. We have used these two papers here. Now I want to go to the green function. Now that we are able to load our ground state to the quantum computer, how we can compute the green function. So I said that a natural operation on a quantum computer is to do the time evolution. So in principle, we could get the green function directly on time. Well, that is not that easy because if you want to do that, you will need to reach relatively very long time with a short trotter error. So that means that in terms of quantum resources, it's maybe not the best thing you can do. Another technique is actually to go back in the past, what people have done to compute the green function. They compute it on the frequency axis. So you can take the time evolution, you do a Fourier transform, and you obtain this quantity. So here we need to invert the Hamiltonian. The Hamiltonian scale exponentially with the size of the system. So, well, that's not great. So what we could do is actually use a technique developed by Longshaws, is to compute the Krivlov basis. The Krivlov basis, we start with this state, C dagger applied to the ground state, and then we apply recursively all the power of the Hamiltonian. And if we if we orthogonalize this basis with the Longshaws procedure, what we obtain is that in this basis, the Hamiltonian is 3-diagonal. And the main consequence is then the green function is just a continuous fraction with the parameters are the alpha and betas of the trigonal matrix. So now we want to do this method on a quantum computer, because on a classical computer, well, the Hamiltonian still scale exponentially, so even doing all the power of h to apply to this state is difficult. So we need to represent our Krivlov basis on a quantum computer. How we can do that? Well, one method is to do that variationally. Like, again, we use an NZAT and we minimize our parameters and represent recursively all the Krivlov state. Another method is to use what is called the quantum subspace expansion. So that's a technique which has been developed by other groups to get the ground state, and we have extended it to the green function. So let me explain you just quickly for the ground state how it works. Well, we want to represent the ground state as a linear combination of some bases. And then we have an equation, the Schrödinger equation, and we project this equation on our basis. What we need to compute here is the H and S, so that's overlap matrices, and because it's like big matrices, we will use a quantum computer to compute these. And then the Schrödinger equation, like that's something we can solve even on, well, probably this laptop. So now we can extend that to the Longshaws procedure. What we need to project here is that the Longshaws equations, but it's the same idea. Like we have some equation that we can solve on a conventional computer, providing that we use a quantum computer to compute these this matrix element. Something I didn't discuss so far is how we can choose these bases for doing the quantum subspace expansion. Well, ideally, the basis that we want is all the power of H applied to our state. But you may be aware that the Hamiltonian is not a unitary operator, so that's not very easy to do on a quantum computer. But something which we can do, which looks like applying the Hamiltonian, is a short time evolution, because it's 1 minus I delta t h. So but if we repeatedly apply the time evolution, we will get all the information that we need about all the power of the Hamiltonian. So our basis will look like the Krivlov basis, and with the quantum subspace expansion, we will be able to describe the Krivlov basis. So that's the basis that we have chosen here. And how to compute the matrix element? Well, I'll go a bit quickly on that because I don't have much time. There are two main options. One is to use the multi-fidelity estimation protocol, and if you want to look exactly how it works, we can look at this reference. If we have, it requires a relatively small readout error, but it doesn't need a control U gate, so that's good. Another option is to use a sort of Hadamard test. It's not exactly an Hadamard test, but then the problem is we need to do a control U on the time evolution, which is actually not too bad because the structure of the Trotter expansion, we can do Hadamard test relatively easily, but it requires obviously a longer circuit depth. Okay, so just to sum up, we start with computing the matrix product state. Then we compile our quantum circuit to get the ground state. We compile with the quantum computer the matrix element, and we get the green function. So we have tested this algorithm on strontium vanadate. So here we have 3 impurities, and we need to discretize the bath site. So just to do the state preparation, we tried with 7 and 17 bath sites. So that means that we have 20 and 40 qubits. Here we just use the Jordan-Wigner transformation to go from fermionic to qubit. And we tested it on a state vector simulator. We use QLAX here. So to convert the tensor network to quantum circuit, longer is our NZAT, obviously better is the fidelity we can obtain, and we relatively easily managed to obtain a fidelity of 99%. And now, depending on the size of the NZAT we use for the ground state, well, we can actually improve the green function. So the dashed line is the exact green function here, and the blue line is the green function that we compute. Here we just do it for 20 qubits because 40 qubits with state vector would be challenging. And better is the fidelity of our tensor network, better is our green function. Can we improve that? The answer is yes, because with the matrix product state, not only we have the wave function, but we also have the ground state energy. And actually, in the green function, we can use the exact ground state energy that we got with the matrix product state, and that's the bottom line here. And what we see is that even with a fidelity of 95%, we already get like a very good agreement with the green function. Okay, so now I would like to conclude. The Anderson impurity model is one of the greatest challenge that we face in real material simulation, and in particular for strongly correlated material. Here we combine tensor network and quantum computing to propose a way to solve this Anderson impurity model, and if you want to have more detail, you can look at these two archive papers. So let me thank my collaborators at NPL, and I will take any question if you have some.
Thank you very much. The session is open for questions and comments.
Thank you for your talk. You solve a fermionic problem on quantum computers. So in order to satisfy fermionic commutation relations for the operators, you need to introduce some strings which may be quite non-local in terms of qubits, non-local operators, a lot of products of Z operators. How do you deal with that?
Sorry, could you repeat?
Yes, you solve fermionic problem on a quantum computer. In order to get proper commutation relations that fermionic operators anti-commute, you need to, say, replace raising and lowering operators of qubit, multiply them by fermionic string. Would it create some problems?
Yeah, okay, so here we use the Jordan-Wigner transformation to go from fermionic to qubit. So that's maybe not the most sexy mapping, but actually the Anderson impurity model is a local model. The impurity is local, so the Jordan-Wigner string is not a big issue. And the issue you may have is with the kinetic energy, but the kinetic energy is a quadratic Hamiltonian, so you can diagonalize it, and that removes the problem when you want to do the time evolution.
Thank you.
Hi, thanks for a nice talk. I'm just trying to understand a little bit the part where you are trying to load your tensor network into a quantum circuit. I'm trying to understand the role of the tensor network here.
The role of what, sorry?
The role of the tensor network. Like why do we load the tensor network into the quantum circuit? Why not just optimize the quantum circuit directly? Because if it works on tensor networks, should we expect that it also works?
Why? Because we know that we can do that on a classical computer. And indeed, we can do the VQE for large system, but then we will face all the problems that we have in variational algorithm like Barren plateau, and that will be difficult. It appears that with DMRG type of techniques in tensor network, they manage to mitigate this sort of problem.
Okay, thanks.
Any more questions? Okay, well, so let's thank the speaker again. And let's thank all the speakers in the morning session.
Let's return here in 1 hour, so at 1:35 to continue the next session.
Error modeling to improve.
Okay, welcome to the last session of the conference, which is about design and modeling. And let's welcome the first speaker of the session, Govia from IBM, on error modeling to improve device design. Please.
All right, good afternoon, everybody. I'm here, like you have said, thanks for the great introduction, and thanks to the organizers for inviting me. I'm here to talk about work at IBM on error modeling to improve device performance, which is a pretty generic title, I will admit. So I'm going to talk actually about a few specific things. This is a little overview of what I'm going to talk about today. I'm going to start with some work we've done on understanding how T1, or qubit lifetime, changes during measurement. And then I'll talk very briefly on some recent work doing error mitigation using characterized device models. And then, of course, I'll conclude and take your questions. So to start with this work on understanding qubit lifetime during measurement, I want to point to this work recently came out on the archive. The listing is there. And this is work with my colleague Ted Thorbeck at IBM, as well as Archana Kamal's group at the University of Massachusetts Lowell, including her postdoc, Zhihao Zhao. And of course, thank you to the funders who allowed this work to happen. So this is an old story, right? We all probably know that T1, qubit lifetime, often changes during measurement. And you can measure this by doing sort of a pseudo measurement pulse, and then doing a strong measurement afterwards to check to see how the qubit lifetime was modified by that pseudo measurement pulse. And typically, T1 gets worse. Here's some great data from another one of my colleagues showing a reduction of T1 on one of our qubits from 270 microseconds all the way down to 70 because of this pseudo measurement tone. Like I said, this is an old problem. But the first experimental papers demonstrating this are from 15 years ago. There's been theory work that followed not too long after trying to explain it. But it's a very frustrating problem because unfortunately, the effect is not consistent. Sometimes T1 gets worse, but sometimes it gets better, and even more confusingly, sometimes it'll do both. Not at the same time, obviously, but do both as a function of, say, measurement power. There have been a lot of experimental scans over the years looking at this, right? All the way up to including some data that I'm going to show you now from us, or well, soon. There's also been a lot of theory work to try to explain this. We go back to the beginning before we had really good isolation between our amplification chain and our qubits, and there was a concern that noise coming from the amplifier would impact qubit T1. But we solved that better isolation. There's great work understanding the phenomenon of dress dephasing, where qubit dephasing noise ends up looking like T1 in a qubit because of the dressing with the readout resonator. But that's also can be fixed by filtering out at the specific transitions that cause this relaxation. And finally, I think, in my opinion, the bulk of the theoretical work in trying to understand this phenomenon has been in looking at modifications to the Purcell decay rate directly. Like I said, there's continuously work on this, but if you have a good Purcell filtering system, this should also be pretty minimized. Now, importantly, like all three examples I've talked about here are looking at qubit dissipation via the readout resonator directly. There are, of course, other suggestions for what might manifest or look like a change in lifetime, even though it isn't directly one, like transmon ionization from the Blay group very recently. And in a lesson as to why you should never model or modify your slides at the last minute, I, of course, have forgotten to mention the great work from Google and UCSB on driven transitions during readout as well, which doesn't directly change the lifetime, but can look like it. But the question that Ted Thorbeck thought about was, but what about the rest of the dissipative environment for the qubit? How does that change during measurement? So we can look at the dissipative environment as a function of qubit frequency doing lifetime spectroscopy, right? Now, we're going to basically just try to measure the T1 time, and we're going to change the qubit frequency either via flux tuning or Stark shift, really depending on your setup. It's a simple experiment, looks like this. In our case, we have a flux tunable qubit that we're going to sweep in frequency and do a measurement to understand its T1. And when we do that, we get something that looks like this. And what this plot of decay rate is showing is that there are these hotspots where the decay rate rapidly increases. And that's likely either due to a two-level system, whatever that may be, or some other electromagnetic mode in the packaging or in the resonators. So then, okay, with that in mind, what happens to the qubit's frequency and line width during measurement? Well, the first thing that happens is we know that there's going to be a Stark shift to the qubit frequency. So whatever qubit frequency we were at originally, omega q, it's going to get shifted to some new frequency, right, by some amount that we can theoretically model under the dispersive approximation, et cetera, et cetera. But moreover, we also know that the line width, there's going to be some induced dephasing due to measurement. That's how measurements work, right? And if you interpret dephasing as uncertainty in the qubit frequency, it leads to a line width broadening. Right? So you can say that, okay, the qubits, it now has this Lorentzian response, right, given by the measurement-induced dephasing rate and the Stark shifted frequency. It's a Lorentzian centered around that. So we can use that to predict how the decay rate will change during readout, right? And so we're going to take this qubit lifetime spectroscopy experiment, and then we're going to use this result from Kaufman and Kurisky from 23 years ago now, where they showed that you could predict the life of the decay rate of a system in a non-trivial environment by an overlap integral between that decay rate as a function of frequency, which we measure with lifetime spectroscopy, and this Lorentzian broadened spectrum. So that's what's the formula shown on the top of this slide here. So we can do that, and now we can actually go and measure the qubit's lifetime during readout through a weak pseudo-measurement tone and then a strong measurement afterwards to check for population that remains. And we can compare that result to the prediction from the Kaufman-Kurisky formula. And that's what's shown on the bottom right here, the blue being the experimental data and the black line the prediction. And that prediction is a function of photon number or photon power that we're pumping through with this pseudo-measurement tone. And the colored arrows indicate the different points represented on the left plot by the Lorentzian shapes, which are indicating the qubit's spectral response at those for those different measurement powers. So you can see, as shown on the bottom left, the qubit gets broader the harder you drive, as well as shifted from its natural frequency without any measurement. So because this is the design and modeling session, I want to briefly talk about the work that myself and Archana's group have done to take the Kaufman-Kurisky result and bring it into a slightly more modern treatment, the Lindblad equation. And what we've done is, when you normally think about a Lindblad equation, you think about some system interacting with an environment. And if you want to formally derive the open system evolution of the system, the first thing you do is to make a rotating frame transformation at the system and bath's intrinsic Hamiltonian frequencies, or you rotate with that unitary. What we do instead, then you can formally eliminate the bath and derive an open system Lindblad equation through the normal approximations, whichever you may want to make. In our case, we are considering a system that isn't a closed system intrinsically. It already has some dissipation. In this case, in our case, it would be the measurement-induced dephasing from the measurement, but we could think of it as any dissipation in some operator A and some rate kappa. So what we do instead is, instead of going to this rotating frame, we define a non-unitary interaction frame by taking the Liouvillean, or that describes the system math interaction, and rotating that by some super operator that includes the full Lindblad evolution of the system itself. And that's what's shown at the bottom equation there. Then you can again go through the same mechanics as you do in the normal case and derive an effective Lindblad equation, where you now have, the system is modified both by a Lamb shift, HS, or HS prime, and some, induced dissipation due to the environment, but it still has its own original intrinsic dissipation shown in blue. But the key thing here is that now this kappa prime is a function not only of the system's Hamiltonian parameters, but also of the system's dissipative parameters, so kappa. And that really allows us to capture the Kaufman-Kuritzky formula in a Markovian Born-Markov approximation Lindblad equation. And we can show that, at least for the situation we are considering, this is indeed still completely positive and trace preserving, but we can't guarantee generically that for any setup this will be the case, or we can't yet. So, given that, like I mentioned, we use this technique to derive, again, the Kaufman-Kuritzky formula that shows that this kappa prime now is some overlap integral of the decay rates at the various as a function of frequency with this Lorentzian spectral response of the qubit. So going back to experiments, we can look at this in a variety of regimes, and we can actually tune between the Zeno and anti-Zeno regimes, because this is what this is, right? It's Zeno, anti-Zeno physics. So in this anti-Zeno effect, where you get a stronger decay rate because of measurement, that's when the qubit has been tuned not initially to some hotspot, so moving away from its operating point gives you worse T1. And that's what the data I showed before. But we can also tune, put the qubit closer to some hotspot, and then we can observe the Zeno effect. Measurement pushes us away from the hotspot, we get less we get less decay, so the lifetime is preserved, hence Zeno. And we can also do both. We can show non-monotonic behavior where the lifetime gets worse and then gets better, just because of the way that the qubit's spectral response traverses its spectrum. And the key insight from the Kaufman-Kuritzky literature is that anti-Zeno is going to be more common, just because more likely than not, you're not going to be operating on a hotspot. You don't want to, right? And then for me, the real smoking gun experiment that this is, at least this model accurately describes what's going on here, is the fact that we can show that the predictions change time-dependently with the spectrum, and it lines up with the experiments. So this is data taken about 9 minutes apart, so you saw that there's some modification now to the qubit spectrum, and correspondingly, the Kaufman-Kuritzky formula, again, predicts different results, and they both agree with the experimental data. So just the conclusion of this part of the talk, I hope I've convinced you that the T1 change during measurement can be somewhat accounted for, at least in this low power regime, by the Kaufman-Kuritzky result. This new master equation construction that we've derived, well, we call it DISCO, for dissipation incorporated self-consistent coarse graining. Hopefully the theory paper will be out in the next month or two. And you can actually apply this to other situations like reservoir engineering when you have engineered dissipation. And we've also been able to validate those predictions experimentally, though I didn't show that data, but you can find it in the archive posting here. Okay, so then very much changing topics. I want to talk a little bit about this recent result from IBM on quantum utility. Right? So I was not directly involved with this work, but I know very well the researchers who were. And the first thing I want to do is really just point out, what did this claim say, right? So what we're claiming here, right, is that we've demonstrated utility at 127 qubit scale, right, where we can measure or calculate expectation values that are beyond brute force classical computation, which just means like actually simulating the Schrodinger equation for the 127 qubit system, right? What we're definitely not claiming is that something like Shor's algorithm is going to be possible without a fault-tolerant quantum computer. That is definitely not what we're claiming. We're also not claiming that the utility is in simulating the Ising model, right? What we're claiming is we've demonstrated an important primitive that is useful in a lot of short-depth quantum circuits, right? And that being the measurement of accurate expectation values. Now, bringing this back towards the theme of this session, I want to talk a little bit about what this paper actually did, right? So it's trotter simulation of this Ising model, up to 15 trotter steps, right? And it uses a technique which was thankfully explained in the previous session called zero noise extrapolation up on our 127 qubits, where we add additional error and then can extrapolate back to what the zero error result should be. I want to point out that with all these recent classical simulations that have come out, there's still about a 20% discrepancy in the actual results that they predict on the hardest instances, and the experimental results lie right nicely within the classical simulation uncertainties. So I think we're definitely competitive with the classical results. Now, again, cycling back to what we're talking about here, this ZNE is implemented in a digital way. It's not implemented by gatefolding, like was discussed earlier. It's implemented by actually probabilistically sampling from the noise of the device that we've learned to implement additional error. Now, that means that we need a really accurate model for the noise, right? And this is 127 qubits. So how do we do that? So first of all, we have to find a way to reduce the error complexity, right? We're talking about a 4 to the 127 noise model, and we reduce that down to only 1,600 parameters or 1,700 parameters. And that's done through a combination of error tailoring by polytwirling, which reduces, basically makes the polytransfer matrix diagonal or reduces the error channel to a polystochastic map. And then we also do model selection. This is the really key and important part, where we only consider error terms in our model that respect the device connectivity, so for connected qubits, and we only think about pairwise interactions, which also respects the device connectivity. So yeah, so finally, I think it's important to acknowledge just the huge amount of people that were involved in this work at some point in their careers, right? It takes a village. But yeah, that's all I had to say today. I hope I've convinced you that error models are needed at all scales of devices, from the dynamics of single qubits, right, all the way up to the biggest devices that we have on offer right now. Thanks for listening, and I'll look to take your questions.
Thank you. Any questions from the audience?
Hi, thank you very much for this very nice talk. And I have a question regarding your first part. So you showed this rotating frame that which includes this Lindblad superoperator. This is the first time I saw it. I feel it super interesting. But my question is that if you want to model this dephasing, a simple way is to assume a dephasing reservoir and assume optomechanical-like interaction, right? That's what Daniel Walsh taught us before he passed away. And my question is, why you chose this difficult way?
So the personal answer is I love master equations, but the more rigorous answer is that doing that enables us to study baths that aren't just dephasing-like. And I don't have any results, theory, or experiment to show that now, but the upcoming theory paper will consider also decay baths, where it becomes harder to apply these other techniques to be able to model their impact on the master equation derivation.
Okay, thanks.
Okay, any further questions?
Hi, thanks for the great talk. I was curious also about the non-unitary frame transform. So I'm interested in whether it was only the no-jump evolution that went into that frame transform, or also the stochastic jump evolution.
It's the full thing. It's the full Lindbladian, so including the jump and no-jump terms.
OK. And really quick, so Zeno, I think, can be still explained by only the no-jump. So do you see something different when you include the jumps?
I think the answer to that is similar to the previous answer. For the dephasing bath, no, I don't. I think you can get at least the majority of the results with just the no-jump evolution. But for the decay bath, or the intrinsic decay, which again hopefully will be out soon, that you need both evolutions to account for.
Okay. Any further questions?
Yeah, thanks for the wonderful talk. Again, I want to maybe ask a philosophical question that you call it Zeno and anti-Zeno because it's measurement-induced, speed up or slow down of the relaxation. But traditionally, the Zeno and anti-Zeno has been thought of arising from the quadratic sort of initial time evolution of a unitary time evolution. But when you start from the Lindblad equation, you have basically forgot about that. You have an exponential decay. So my question is that, is there something, is this kind of is this related to the traditional Zeno effect concerning that, or is this, you just call it a Zeno because you get this from the measurement?
Yeah, I think there is a little bit of overloading of the terms, for sure. The Kaufman-Korisky results that we're quoting, where we consider the anti-Zeno and Zeno in a variety of atomic spectra, they did do, in some sense, an exponential approximation to that short-time quadratic evolution, and that's where those formulas come from as well. They're just from a different approach to derive them. So yeah, personally, I don't really have an opinion as to whether this is truly Zeno or anti-Zeno, but I know that it's not, maybe not the most textbook way of using the terms, for sure.
Thanks. Also about the first half of your talk, you end up, it looks like you end up with these sort of correlated noise processes, and you can think about diagonalizing what's called a Kosakowski matrix, and you end up in that case, if you do it sort of fully self-consistently, with terms that look like Lindbladians, but other ones that look like Lindbladians with negative signs. That is, they're not really Lindblad operators. Do you get those in your derivation?
Yes, you do, and the theory paper is out soon, and we will have examples of that. Yes.
I guess, yeah, there's still.
So do you change your readout strategy, like how many photons you're using, or like how strongly you're doing the readout based on like where these TLSs occur near your qubit?
So this is pretty fresh results, right? Even internally, and I think it's made us definitely reconsider what the optimization parameters should be for high performance readout. I think one takeaway message that actually Ted really tries to emphasize is that the qubit doesn't have one frequency. You should really be thinking about a window in frequency around your operating point. So it's still, I think, to be determined how much we change things as a result of these effects, but it's definitely something we're considering.
Thanks.
Okay, thank you. We are for to keep the schedule. Let's continue the discussion afterwards, and let's thank the speaker again. Okay, and let's welcome our next speaker, María Hita-Pérez from CSIC. The topic is capacitive coupling of persistent current qubits. Welcome.
Okay, so thank you for the introduction. My name is María Hita-Pérez, and today I'm going to present our work on the capacitive coupling of persistent current qubits, which is summarized in these 3 papers over there. In these papers, we propose several superconducting circuits architectures which could be useful for the implementation of novel interaction models for quantum technologies. So let me start with the first proposal, which is the capacitive coupling of flash qubits, which could be useful for the implementation of non-stochastic effective Hamiltonians for adiabatic quantum computation. So, what is adiabatic quantum computation? Adiabatic quantum computation is an analog computational model which takes advantage of the adiabatic theorem to find the solution to a certain problem. So how does it work? We have an initial Hamiltonian, H0, whose ground state is known and easy to prepare, and a final Hamiltonian, HF, which is our problem Hamiltonian. We encode the solution of the problem that we want to solve into the ground state of this Hamiltonian. And we also have an interpolating Hamiltonian between them. We assume that these Hamiltonians can be implemented into a quantum device, and then the procedure goes as follows. We initialize the device into the known ground state and easy to prepare ground state of H0, and then we make the system evolve following the interpolating Hamiltonian till we reach the problem Hamiltonian. Provided that this evolution is performed slowly enough for the adiabatic theorem to apply, the system stays in its ground state during all the evolution. This means we initialize the system in an easy-to-prepare ground state, and we end up with the ground state of the problem Hamiltonian, which encodes the solution to our problem. So I have said that we are particularly interested in implementing non-stochastic Hamiltonian for these adiabatic quantum computation procedures. But why non-stochastic Hamiltonians? A quantum Hamiltonian is stochastic in a certain basis if its entries are real and each of the Agarwal elements are non-positive. The main consequence of this definition is that these Hamiltonians do not suffer from the same problem. This means that, in principle, they can be solved using standard Monte Carlo methods. On the other hand, we have non-stochastic Hamiltonians. These Hamiltonians do suffer from the same problem and cannot be simulated efficiently. Implementing these Hamiltonians is intrinsically interesting for two reasons. First, because they can be used to simulate other quantum systems that suffer from the same problem. And second, because they have been shown to enable universal computations when used for adiabatic quantum computation. So, in our work, we propose different circuits to implement these non-stochastic Hamiltonians. Basically, we study the capacitive coupling between a flash qubit and another flash qubit, and between a flash qubit and a resonator. So, particularly, we choose to use 3 Josephson junctions flash qubit. A 3 Josephson junction flash qubit consists of a superconducting loop interrupted by 3 Josephson junctions, 2 of them identical and 1 of them alpha times smaller. The important property of this system is that when the external flux equals half of the flash quanta, it develops a double well potential with 2 opposite sign current states, left and right, whose symmetric and antisymmetric superposition are the ideal candidates to form a qubit. Hence, the effective Hamiltonian of the system is this basis, is the typical qubit Hamiltonian, where delta is the gap between the energy states. So we want to couple 2 of these flash qubits. To do so, the first thing that we have to do, and we want to find the effective interactions. To do so, the first thing that we have to do is to choose a way to model the full Hamiltonian of the system with the 2 Hamiltonians of the different qubits and the interaction into an effective Hamiltonian in terms of Pauli operators. We do so by means of the Seifert-Wald transformation, which maps eigenspaces of the full Hamiltonian into eigenspaces of the bare Hamiltonian without the interaction. Provided that the subspace of the system can be divided into 2 different subspaces, a high energy subspace, which we call Q, and a low energy subspace P, which in our case is composed by the 4 lowest energy levels of the system. This is the composition of the 2 qubit bases. So, we use this Seifert-Wald transformation to derive the effective interactions using 2 different procedures. First, we analytically derive the interactions following the typical perturbation theory, and then we numerically calculate the interactions following the non-perturbative procedure used by Consani and Warburton in that paper. This method allows for obtaining the exact effective interactions only using the projectors into the low energy subspace, P0 and P, the Seifert-Wald transformation, U, and the Hamiltonian of the system, H. The main issue with this procedure is that it is computationally expensive since the computational cost grows rapidly with the number of elements of the circuit and the dimension of the elements. So to avoid this obstacle, we propose another method to compute P0 UP, just in terms of the projectors into the low energy subspace. And it requires only the extra calculation of a singular value decomposition. This way, we reduce the computational cost of computing the effective Hamiltonian to that of finding the low energy levels of the system, which can be done efficiently. So we want to couple 2 flash qubits using a capacitor. We find that the effective Hamiltonian for this system has this form, where the 2 first terms are the single effective qubit Hamiltonians with a gap that is renormalized by the interaction, and the last term gives interactions in 3 different directions, sigma x, sigma y, and sigma z. So this is exactly what we find. We find a strong renormalization of the qubit gap with the increasing capacitance and interactions in the 3 different directions. For small values of the capacitance, we find a prevailing sigma y contributions, which fulfills our expectations of finding interactions between the charge in the 2 flash qubits, and then when increasing the capacitance, we see that the other terms gain the strength. We find a sigma sigma-sec contribution, which accounts for interactions mediated by high energy states, and a residual sigma-s contribution, which is related to intercept tunneling and comes with an enhancement in church noise. All these contributions depend on the flux parameters and the system parameters. Okay, so these results suggest that we could combine the capacitive interactions with the widely studied inductive interactions in order to find non-stochastic Hamiltonians with arbitrary interactions in the three different directions. Another approach to the coupling of the two flux qubits is using a resonator to mediate these interactions. In this sense, we study the capacitive coupling between a flux qubit and a resonator, and we find that the effective Hamiltonian has this form where, again, the first term is the Hamiltonian of the qubit with a gap that is renormalized by the coupling. The second term is the Hamiltonian of the resonator, and the last term gives interactions which are perpendicular to the ones that we find when studying the inductive interaction. This last term provides evidence of ultra-strong coupling between the qubit and the resonator with magnitudes above 12% of their energies. So for this first part, we have derived a complex set of Hamiltonians, finding evidence of ultra-strong coupling and non-stochasticity. We think that these Hamiltonians might be useful for universal adiabatic quantum computation. Okay, so let me move on to the next part of this talk, in which we saw that a bound state in the continuum appear in this device. So first of all, what is a bound state in the continuum? A bound state in the continuum is a localized state that lives in the continuum of energies. Contrary to what happens to resonance, the special characteristic that this state has is that they don't eventually decay into the continuum of energies. They mean that, in principle, they have infinite lifetime because they are decoupled for the continuum of energies, maybe by symmetry or interference between resonances. So, in our work, we propose to construct an scalable and compact bound state in the continuum in the second excited state of a fluxonion that is coupled to a waveguide. This is motivated by this experimental result by Manoucharian and his team. In this work, they find that at zero external flux, the transition between the second excited state and the ground state of the fluxonion is forbidden. So we consider a fluxonion, but we consider a fluxonion at external flux equal 0. For this value of the external flux, the system develops a three-well potential such that the global minimum of the potential corresponds to the ground minima, to the ground state of the system, and the antisymmetric and symmetric superposition of the two local minima correspond to the first and second excited states of the system. So we couple this fluxonion to a waveguide, and we find that the interaction term has this form, where the relevant operator is the Church operator. This lets us prove that there exists a bound state in the continuum, in the second excited state, simply by showing that we cannot mediate transitions with the Church operator in and out of the second excited state. This is kind of evidence for the transitions between the second excited state and the ground state, because the Church operator is an antisymmetric operator and cannot hence mediate interactions between two symmetric states. But this is not the case for the transition to the first excited state. However, we find that for certain values of the fluxonion parameters, we still have a really long-lived state in the second excited state. We study the transition rates between the second excited state and the first excited state of a fluxonion, and we see that for less radius between the Josephson energy and the other characteristic energies of the system, we still find decay rates that let us say that the second excited state is a quasi-bound state in the continuum. In fact, we find lifetimes of the other order of seconds. But is it really that long-lived? Ideally, no. Ideally, yes, but we have to consider other decay mechanisms that could produce the decay of the bound state in the continuum. We consider three types of mechanism. First, the effect of non-zero temperature in the waveguide, which could mediate transitions to high energy states. The effect of non-zero external flux. Rigorously speaking, the symmetry that protects our peaks only exists at external flux equal to 0. This means that flux fluctuation could activate the decay between the transition between the second excited state and the ground state. And last, we consider interactions with the environment. We consider dielectric losses, inductive losses, and 1/f flux noise. I don't have time here to explain all about this, but I'm going to focus on the dominant decay mechanism at low temperatures, which is the 1/f flux noise. Contrary to what happened when we were studying the transition between the second and the first excited state, we see that in this case, going to the regime of the heavy fluxonion strongly decreases the lifetime of our bound state in the continuum. Nevertheless, carefully choosing the values of the parameters of the fluxonion, we still find lifetimes of the order of 0.1 milliseconds. So for this second part, we have shown how to construct a compact bound state in the continuum with lifetimes of the order of 0.1 milliseconds and large sensitivity to flux noise. We think that this device could be useful for storing protected quantum information and also as a magnetic field sensor. So this is a summary of my talk. And I want to conclude presenting my group. We are the Quantum Information and Foundation Group, and this work has been made in collaboration with Pedro Orellana, Gabriel Jaume, Manuel Pino, and Juan José García Ripoll as part of the European project Abacus. So thank you all for your attention. I will be glad to answer any questions.
Thank you. Any questions from the audience?
So thank you for a great talk. I'm not so well understand the relation between the fluxonium qubit and the non-stochastic AQC or yes, and the first part and the second part. So is there any relation between the non-stochastic computing for using the fluxonium? No.
In principle, from our studies, we don't see any relation. But the truth is that the fluxonium is used as a qubit, so maybe it would be interesting to study the interactions between fluxonions to see if they could be used for non-stochastic adiabatic quantum computation.
I think, and also, sorry, the previous question is not so good. For non-stochastic quantum computation, in my understanding, that JXX and JYY is also should be tuned separately, right? In that case, it seems very difficult to implement in the real circuit. So, do you think about these kind of things?
Yeah, it was also one of the conclusions of this work that maybe it is not as easy as we thought when we saw like the paper of Fidan et al. Where they studied this they found experimentally this non-stochastic coupling, that maybe you cannot tune the sigma YY and the sigma XX contribution separately. So we have to take a look, to take a deeper look into this. Yeah.
Thank you.
There's one, I think, up there.
Hi, thanks for the nice talk. One question to your Schrieffer-Wolf transformation method. So usually there are some truncation when you do the Schrieffer-Wolf transformation on systems like that. So is this like a complete approach, or did you some truncation, and did you also check for higher order corrections here?
No, we didn't do any truncation. The thing is that when Consani and Warburton use this Schrieffer-Wolf transformation, they have to truncate the Hamiltonian to use it. But since we only use the low energy eigenspace of the system, we can just like tell our program, just calculate the 3 lowest energy levels, and that's it. We use that, and the transformation is exact. There isn't any approximation.
Okay, I see. Thank you.
You're welcome.
I don't see any further requests for questions, so let's thank the speaker again. And the next one is the last speaker of the conference, Abhishek Agarwal. I hope I got the pronunciation even close, from National Physical Laboratory, and the topic is modeling non-Markovian noise in driven superconducting qubits. So welcome.
Good afternoon, everyone, and thank you for the introduction. Yeah, I'm Abhishek from the National Physical Laboratory in the UK, and I'll be presenting some of our team's recent results on modeling non-Markovian noise in superconducting qubits. Let me begin by motivating why we want to do this, although we had a great talk by Luke earlier, so I'm not sure I need to spend a lot of time. But modeling noise can allow us to learn about the sources of errors that are present, improve qubit calibration, develop methods to mitigate noise, and also estimate the confidence that we can have in the results. Now, existing methods for modeling non-Markovian noise that we have today, they're quite expensive in terms of the number of circuits that we need or the total time we need to run these characterization experiments. So that's why there's a need for new methods and models to understand the non-Markovian noise affecting our qubits. In this work, I'm just focusing on the single qubit results, but some of these can be generalized to more qubits as well. OK, let me talk about our method for noise characterization. And our method involves the use of pseudo-identity operations, which are operations that should result in just the identity if you don't have any noise in your device. So to give you some examples, ideally, if you just leave the qubit idle and not apply any gates, that should just be the identity operation. Or, for example, if you're doing 4 90-degree rotations, should be the identity, but if you have, let's say, a 1-degree over-rotation, then you can see that the over-rotations will add up, and you'll have a 4-degree over-rotation. Or you can have a general theta rotation and then a minus theta rotation, which should, in the absence of any noise, it should be the identity, but you may not have identity because of noise. Now, the reason we're using these pseudo-identity operations is that repeating these operations amplifies the errors that we get. So for example, taking the example of the over-rotation error, if we do 4 90-degree gates, but we have a 1-degree over-rotation, at the end of one pseudo-identity, we will have a 4-degree over-rotation. But now when we repeat that, that keeps on adding up. So we'll have 4-degree over-rotation, 8 degrees, 12 degrees, and so on. And once we've amplified the noise, it makes it easier to actually characterize the effects of the noise. Another reason why they're interesting is that different pseudo-identity operations amplify different kinds of errors. So I've talked about over-rotation, which, for example, is amplified by doing 4 90-degree gates. But if you're doing a theta and then a minus theta, you can see that the over-rotation error would be canceled out. But there's other kinds of noise which would be amplified by one sequence, but not amplified by the other one. In this work, we're mainly interested in using pseudo-identities of the third form shown here. And the reason is we can actually sort of ignore over-rotation errors and some other errors and just focus on, well, you'll see non-Markovian errors that we obtain. Now, we implement an arbitrary theta rotation by just changing the amplitude of a pre-calibrated pulse. So in this case, the pulse that was calibrated on the device was a pi-half pulse. And to do a general theta rotation, we just change the amplitude of the pulse linearly. So I've described the pseudo-identity, but the whole circuit is shown here. So we start with the qubit in the 0 state. Then we do a state preparation operation. So the Y gate here prepares the qubit in the plus state, so on the equator of the Bloch sphere. We then repeatedly apply the pseudo-identity, so that's shown in the dashed box here. And inside each pseudo-identity, you can see we're applying 4 X gates here. And the difference between, well, let me use the pointer. Yeah, so the reason why we're doing 4 of these followed by 4 of these is just so that we don't have to apply pulses with very large amplitudes. And to implement the negative theta rotation, we're interleaving these operations with virtual Z gates. So these virtual Z gates effectively just convert the theta rotation to a negative theta rotation. And finally, after we've repeated the pseudo-identity n times, we perform measurements in the x, y, or z basis by applying a pulse to change the measurement basis. So here are some of the details of the experiments that we've run. So we've run them on a single qubit IBM quantum device called IBM ARMONC. The value of theta, which essentially controls the pseudo-identity gate, ranges from 0 to 3 pi. So the case of 0 is just leaving the qubit idle. But the case of 3 pi is doing a 3 pi rotation, then a negative 3 pi, then 3 pi, negative 3 pi, and so on. And we range from 0 pseudo-identities all the way to 150 pseudo-identities. Now, when we're running these experiments, we need to send the circuits for execution in different batches. And because of limitations in how many circuits we can send in one batch, in each batch that we send, we include the circuit for one value of theta full. So for example, let's say pi over 5. But we also include the circuits for just the idle qubit. And the result for that will become apparent later. Now, we run all these circuits on over 18 consecutive days to gather some data. And then we fit different noise models to the data to actually see how our models are performing. OK, let me now talk about the different noise models that we have. And I'll begin by talking about just the Markovian model. And there's many different important sources of noise that we haven't included. But for the purposes here, we have a phase error on the qubit, which leads to oscillations about the z-axis. And this can occur, for example, if you haven't calibrated the qubit frequency correctly. And we also include the traditional dephasing and amplitude damping noise. So these three noise sources together will be forming what I'll be calling the Markovian model. I've mentioned non-Markovian a few times without actually defining what it is. And there's many different ways to actually define it, but for our purposes here, if we can model the qubit environment interaction with a memory-less environment, then we have Markovian noise. But if we need to allow the environment to actually have a memory or sort of remember the previous qubit states, then we have non-Markovian noise. Now, there's interesting properties for each of these. So with Markovian noise, what we see is that if we look at the property of some qubit observable as a function of time, we only get single frequency oscillations as a function of time if you have Markovian noise. But with non-Markovian noise, you can actually get multi-frequency oscillations of qubit observables as a function of time. Also, there's another interesting feature, which is that the qubit purity can oscillate. So the qubit purity measures how pure the qubit state is. And we can go from the qubit being completely pure state to a maximally mixed state, back to a pure state, and so on. So these are some signatures which we can use to detect the presence of non-Markovian noise. OK, but how do we actually begin to model this kind of noise? In this work, we're introducing non-Markovianity by letting the qubit interact with a quantum two-level system. So in the schematic shown here, we have the qubit, which interacts with the bath, and this leads to dephasing and amplitude damping. But it also interacts with a two-level system shown here. The Hamiltonian for this is shown in this equation here, where you can have the first term corresponds to the phase error on the qubit. And the second term is the qubit TLS interaction strength, which is parameterized by this variable nu here. In this model, the TLS is initially in the 0 state. And I mentioned that we only obtain non-Markovian dynamics because we're looking at the qubit subspace. If you look at the dynamics of the whole thing, then we still have Markovian behavior. But by tracing out the TLS, we can get non-Markovian noise. Now, this is physically motivated because we had a couple of talks as well. TLSs are obviously a very important source of noise. And there's also a few papers which have found even one or two strongly coupled TLSs really affecting the qubit performance. In terms of the model parameters, the Markovian model just has 3 parameters. So that's the phase error, delta omega, dephasing, and amplitude damping. But the qubit TLS one has 1 additional parameter, which controls the qubit TLS interaction strength. I mentioned now that this model is still only an effective model, and the reason for that is there's actually a different kind of physics that can be used with this model. So the physics implied by the previous slide is of a qubit interacting with a coherent TLS, but actually it can also work with a qubit interacting with a thermal fluctuator. So just to give some more details on that, let's say that in the absence of a TLS, the qubit frequency is omega, but in the presence of a qubit TLS interaction, the qubit frequency can shift by a value nu. And this TLS fluctuates between the states, so the qubit frequency is effectively fluctuating. Now, when we're calculating some qubit observables, we run the circuit, let's say, 1,000 times to calculate the observable. If this TLS is fluctuating slowly, so slow is slower than the time for 1 shot, but still faster than the time for 1,000 shots, then we might have that half the time, so roughly 500 shots, the qubit had 1 frequency, half the time the qubit had a different frequency. And in this case, the results that we obtained for the qubit actually identical to the model that I showed on the previous slide. And we have some new results, which I'm not showing today, but which show that actually the noise that we obtain on the IBM device correspond to the noise caused by these 2-level fluctuators. OK, finally, I'll move on to some results. So here I'm just showing a representative example of the idle qubit dynamics that we obtain. So here, the x-axis is the number of pseudo-identities, which in the idle case is effectively just the delay time. The y-axis are effectively the coordinates of the qubit in the Bloch sphere. So we have the x, y, and z coordinates in the Bloch sphere. And lastly, we have the qubit purity. The crosses denote the experimental data, and the dashed line is just an interpolation. What we can see is that, firstly, we clearly have multi-frequency oscillations, which was one signature of non-Markovian noise. And we also have oscillations in the qubit purity, which was the second signature of non-Markovian noise. So this shows that, OK, we do have some amount of non-Markovianity in the qubit. Now we can look at how our noise models perform. So we fit our noise models to the data. And here, the blue result is the Markovian model result, and the orange is the qubit TLS result. And I very quickly summarize this. So you can see the blue one doesn't fit the data very well, but the orange one fits it very well. So this shows that, OK, our model can capture the non-Markovian effects seen in the data. Now, we've gathered these data at different times, so we can actually look at the stability of the qubit dynamics. So here I've just plotted one qubit observable, so that's the x coordinate in the Bloch sphere. And these are all the same experiments run over the time span of half an hour. And you can see that sometimes the results look similar, but sometimes they look very different. And just by visually looking at them, we can group them into results that look similar. So those are the ones in the same color. But we also have these very abrupt changes. But we can actually go further and analyze what's causing them by looking at the model parameters. So here I've plotted the phase error of the qubit, that's shown in blue, as a function of time, and also the qubit TLS interaction strength. And we can see that when we had this abrupt change in the dynamics, for example, green to red, we also have a significant change in the qubit TLS interaction strength. So what this is showing is that the instability in the qubit dynamics is being caused by this non-Markovian noise. We don't know the reasons for the change, but there's papers which have looked at interactions with other TLSs, cosmic rays. So there's lots of different explanations for why we have this instability. Lastly, let me talk about some of the results with the driven qubit. I won't spend too much time on this slide in the interest of time, but I'll just say the different columns here correspond to the different values of theta, so effectively different pseudo-identity operations, and the different rows are the different coordinates. The main conclusion that I want you to take away is that in all the results, the Markovian model doesn't work too well, but the qubit TLS model works very well throughout. And interestingly, we also see that the qubit dynamics can change quite significantly because we're applying these different pseudo-identities. And this is a good test for the model, so the model seems to work for all these results. Okay, I've just seen that I'm out of time, so this is my last slide, and I'll try to be quick. Because we applied the different pseudo-identities by changing the amplitude of the pulses, we can now look at how the noise changes as a function of the pulse amplitude. In these graphs here, I've shown essentially the phase error as a function of pulse amplitude. And we can see that it changes quadratically. And this can be explained by the Stark shift, the Stark effect. And here I also plotted the qubit TLS interaction strength. And this also changes with the pulse amplitude. We don't have an explanation for the exact trend here. But by doing some more analysis, we can actually try to investigate and understand the physical source of noise causing this change. Finally, to conclude, we've developed methods to characterize non-Markovian noise. Our experiments reveal significant non-Markovianity, and we've seen that we can successfully model it with the qubit TLS model. We've seen some rapid fluctuations in the qubit dynamics, and we found that we can attribute them to the instability of the non-Markovian noise. And analyzing how the noise changes as a function of pulse amplitude can help us learn about the source of noise in the device. Finally, these methods and results can be used to obviously learn about the noise, but also improve qubit calibration and implement error mitigation strategies as well. Lastly, I mentioned, and in parallel, we're also working on scalable noise models. So we had a good talk about this a couple of talks earlier, including, for example, crosstalk noise in the device. With that, I'd like to acknowledge my co-authors, and yeah, thank you all for listening.
Thank you. Time for questions.
Thanks. Excellent talk. Really great talk. So you said the the theory plots you showed were for the TLS model, not the fluctuator model. So what were the parameters of the TLS model? And what was the initial state for the TLS with the data that you showed, or the fit model that you showed?
So could you repeat your question?
What were the parameters of the TLS model, and what was the initial state of the TLS for the simulations you showed?
Yeah, that's a good question. So in order to get non-Markovian effects, we need the TLS in this model to be in a superposition. Well, okay, depending on the form of interaction that you choose. So here, for example, we have a ZX interaction with the TLS. And in that case, to obtain non-Markovian effects, you need the qubit to be in, for example, the 0 state. But if we chose a ZZ interaction, then we would need the TLS to be in a different state. And this kind of shows why it's only an effective model, because there's different Hamiltonians and initial states that can still give you the same results. So for example, as I mentioned, you get the exact same results whether you choose this model or a fluctuator model.
Thank you.
When you were showing the gates, you said you would do the 4 times 1 and then 4 times the inverse. Why weren't you alternating them? Why did you choose to do 4 at a time?
That's a good question. So the reason is, let's say we want to do 3-pi rotation and a negative 3-pi rotation. We can either do that by applying just one big pulse that does a 3-pi rotation, or by 4 smaller pulses that together do 3-pi. And the reason for breaking it down is essentially, if we have very large pulse amplitudes, we can introduce additional errors into the system. And also, the linearity of the rotation amount with respect to the pulse amplitude can break down. So that's why by limiting the amplitude of the pulses, we can sort of try to stay away from those kinds of additional errors.
Thanks for the talk. So building on the previous question, are there like specific gate sequences that would probe specific types of noise, and is that unique? Like, you know, spin echo you can use to probe, yeah.
So could you repeat the question?
So the question is just, is there specific gate models or unique gate sets that you would do, which are pseudo-identities, that would probe specific types of noise?
Yeah, exactly. So let me give a quick example. I glossed over this, but yeah. So if you look at the results here, you can see that we get quite different results for the different columns. So these are the different pseudo-identities. If you look at the fourth column, which is doing 2 pi and negative 2 pi and so on, we can see that we barely see any oscillations. So this is the case where a lot of the noise is completely canceled out. And the advantage of having is sort of this continuous pseudo-identity, which is parameterized by this theta, is you can actually, by looking at different pseudo-identities, you can make sure that you're sort of covering your bases by making sure the model works for these different kinds of noise effects. But it's still not the whole picture, right? So for example, over-rotation errors are completely canceled out in all of these. So you would still need like more experiments to fully characterize the noise.
Okay, thank you. Let's thank the speaker again. And also, let's thank all the speakers of the conference. It's been a great experience. And time to close the scientific discussion here, the official part. And I believe the next, there will be closing remarks from Ekaterina and Klaus, if I understood correctly. And let's move into that part. Please, welcome.
Thank you. Oh, you almost did it. We're the last step between you and freedom. 4 days of conference has been amazing.
Great experience, for sure.
Yeah, I always think it's amazing. You think it's 4 days, so much of time, and then it just goes by in the blink of an eye. Still, we want to take the opportunity to take you back again through the last 4 days, show you a few of the highlights, and maybe also tease you a bit about what is to come. And who's going to do that? That's us. That's me, Klaus, and Ekaterina. And I'm going to deter here from the script a bit, Ekaterina, because I wanted...
That's what I expected.
I wanted Ekaterina is properly introduced to all of you, and she has been a bit, let's say, the mastermind behind the conference. Always in the back of the stage, pulling the strings. And I would say, fitting to a conference on qubits, you are like the real-life image of a qubit. Whenever I would not measure you and see where you are in a superposition, organizing all the aspects of the conference, everything all at once at the same time. Really amazing. And for that, please give her a long round of applause.
Thank you so much. Thank you. I must, is it working? Yes, I must say they didn't tell me anything about that, so thank you so much. It's a great appreciation for my work and also for the work of the whole team, because of course it's not only my contribution, it's also the contribution of all those people from IQM, from TU Munich, from MQB, who have been working tirelessly to make this happen for all of you. So that's why thank you so much.
So, Ekaterina, do you want to start us off and tell us a bit about our nice conference, about how you experienced our community?
Yes, indeed. So representing the SQA organizing team, it's of course a great pleasure for me to be on this stage now, and having all of you in this audience and many more following the live stream online means that we have achieved the purpose that we have set at IQM when we were starting this event, meaning we have created a platform where academia and industry could meet, exchange, and create together, because passion for science and knowledge is something that we all share.
Thank you. Yeah, and really everyone, right? I mean, all the scientists and all the companies alike. And I think this is something super important, which SQA Conference does in a very nice way. Navigate this fine line, because we need both aspects. We need the companies. Thank you again. Thank you so much to all the sponsors, because the conference could not have happened without you. It is really awesome. Thank you also for being here, present at the conference, down that exhibition booth, making sure to give all of the scientists the opportunity to engage with you and learn from you. And it's also a showcase for us that SQA really delivers something, because so many companies decided to use SQA as the platform to announce their new line of products, ranging really the full stack of the superconducting qubit quantum computer, from the cryostat to the hardware of the controlling and the readout apparatus, all the way up to the new software products were presented at this conference, which is really amazing. It looks like we are having now paved the way for scale up. The only thing that's missing is apparently just a few million of qubits. How hard can that be? And of course, this ties over neatly to the other part of the conference, the scientists. We learned so many amazing things about superconducting qubits and the newest developments in the field. Starting all the way with the challenge of how to design new qubits in such a way that the errors can be easily corrected, going over the advantages of different distance codes, the quest that they can really improve orders of magnitude and the need for understanding the error budget correctly. New fabrication technologies that's now really able to do 3D integration and build tier 3 stacks where the qubits become better in terms of lifetimes and reduced crosstalk. And we even heard amazing features about optical transduction, where it's now possible to do readout with photonic interconnectors. So really amazing features that have been presented to us. And I cannot mention all of them. There have been so many great talks, especially from the young generation, showing us that there's a really increasing interest in the field, all the way from the experiments of doing reset up to the way to the deep down theory of visualizing state tomography. It's really been awesome. Also something which is super close to my heart are the poster sessions. This is always amazing to see how people talk to each other, get into heated discussion and have the chance to really dig down into aspects of certain scientific prospects and live the discussions. Wouldn't you agree?
Absolutely. We have indeed witnessed heated discussions both in this conference hall and also outside of it, and they lasted until late in the evening. But I think that one main challenge actually remained unnoticed. And I would say that this challenge is the shortage of quantum talents that both industry and academia start experiencing already now. That is why one of the big purposes for the SQA conference would be to empower your career choices in quantum physics. And I would like to give a special appreciation to young scientists who joined us both here in person and online, because that conference has been made for you. And of course, another big part of what we are trying to achieve with the SQA conference is networking, because focus on superconducting qubits and algorithms allows us in-depth discussions and collaborations. And those in-depth discussions we would like you to continue after you leave this conference hall today. That's what we would like to cherish and grow further behind those walls. And also a special thank you again to our supporters, because it's 24 companies who joined the exhibition floor this year. We have also introduced a new format of workshops where they have shared their first-hand experience on best practices in their field. So I think this should be very practical to the young specialists in the field as well.
Definitely.
And of course, last but not least, the point of the conference was to introduce you to the beautiful city of Munich, its culture, and also its vibrant quantum ecosystem with the side events supported by Walter Meissner Institute, Leibniz Supercomputing Center, and QTRA. So thanks a lot for doing this. I think it has been a really interesting program that enriched myself a lot, because I visited Leibniz Supercomputing Center, and that was the first time, and that was just an amazing experience. So, yeah.
Do you want to mention a bit about the social networking and our LinkedIn account?
Is it me again? Okay, sure. Yeah, of course. Now I think it's time for thanking right? Because that's where I planned it, but maybe we can improvise a little bit, and I can start with thanking you for your social media activity, because it has been really amazing, and for all your shares and retweets and likes, thank you so much. That helps us to spread the knowledge and to engage more people. Thank you.
Yeah. Really, thank you. Especially, you did it during the conference. I'm sure many of you will also do it after the conference. Tell everyone about how great experience you had after SQA. After SQA, yeah. There's this very, very famous proverb, after SQA is before SQA. Yes, of course, right? SQA is going to continue. We're going to have an SQA Conference 2024. And actually, we want to make sure that it's a really awesome conference that's going to happen. And what we're going to do, therefore, is we're going to send out a feedback form to all of you. You're going to receive it in a couple of half an hour, 10 minutes, 15 minutes per email.
And that's me who will send it. So.
Please take the time, have a look at it, and fill it in. Because we want to make sure that this SQA continues to be an awesome experience. And for that, we need to know what you want. Do you like our balance between science and industry? Do you like the size and the scope of the conference? Tell us what you want so we can make sure that you like it. Well, I think I know one thing that you want to know for sure. The place where next year's conference is going to be, which is going to be, I cannot make it that easy, can I? We got yesterday already in the spirit of the pub quiz, right, with our nice qubit hunt. Don't worry, you don't have to answer any questions, but maybe try to figure it out while I talk along in the next 1-2 minutes. I mean, for sure, what do we need about a conference? We want to understand the quantum nature, the quantum wave function of our qubits. So we need to have waves present, right? So somehow water needs to be present at a conference. Then at least water waves are there.
Any guesses?
Of course, well, not of course, but we have now this color scheme for so long of blue and green. Maybe we can introduce some new colors, something more bright and vibrant. Well, who knows? Could be an idea. It's not fixed yet, but we're going to discuss it. And then there's also the question always, what is really the best architecture for our chip? We want to go to a place which gives us proposals, like should we really do a grid structure? Is there somewhere where we see places around there which feature that? Well, is there anything else? I mean, maybe a city which has some weird kind of infrastructure, some kind of art which is presented somewhere. Some weird things suddenly in the middle of the street. Well, okay, let's be a bit honest and show you a bit more. Let's have canals, lots of canals, the city where we're going to. It has flowers, a very special kind of flowers and abundances of them. And it has windmills.
We have a guest there.
It's going to be Chiew. Yeah, I see a lot of confused faces. TU Delft seems to be not so well known. Actually, the people from TU Delft approached me and said, oh, we are afraid that nobody's going to understand why TU Delft. And so we said, okay, you know what? You can come up on stage for a minute and tell us why Delft is really a good opportunity. I welcome on stage Christian and Amber from TU Delft.
Great, thank you. We thought it was best to have two non-Dutch people represent Netherlands. So we have myself and Amber.
Hi. Well, I think you should start because the academic history is kind of the most attractive thing about Delft, and I'll give some extra arguments afterwards.
Yes, great. So I will start telling a bit about why we think Delft is a good place to do science, or quantum science in particular. There has actually a really good history in quantum, as you may know. We just had a few talks ago, a little bit about flux qubits. Some of you may know that the first flux qubit was made just next to the building you see in the picture. So it's pretty cool. And we do a lot of quantum science. The first loophole-free bell test was done also, that place. And more recently, we had in Delft the first cloud quantum computer in Europe, in Delft, which was both superconducting qubits, which we all love, and also spin qubits. And now we have a quantum institute, which do a lot of quantum. I could go on about numbers. One thing I do like is we have 42 cryostats in the building. I don't know where all of them are, but it's a good number. So it's a good place to do science. And we hope that we can all come there and then discuss science, because that's cool. Amber.
Yeah, so next to amazing science that happened over the past decades, I think you didn't mention Hans Moy and his contributions, but next to that track, there is also, in more recent years, technology development, and even on the commercial front, product development that has started up, also directly supported by the Dutch government, really a focus on quantum with the funding of the Quantum Delta NL organization. And I think, so if you're not convinced yet by the scientific part, which is going to be super interesting, also come to see the technology and implementation in products. And maybe as a last thing, it's also a really nice place to visit. So it's like Amsterdam with just as many bikes and canals, but without all the tourists. Unless, we managed to scale it even too much. But so we hope to welcome you from the scientific community there, as well as the ecosystem that's developing around that. And we very much look forward to hosting you in a successful conference there next year.
Yeah, Delft, it's a place with old churches and new technology. It's amazing.
Thank you so much. Thank you especially for taking away now the organization from me. It's very good, we have found a new victim. And to scare you a bit in advance, you maybe don't realize yet how many people it really takes to organize such a conference. Ekaterina, shall we tell them?
Absolutely. Let's come to my favorite part. And those of you who are part of the organizing team, I would like to ask on stage for the round of applause, because I think it really has been your contribution that made this happen. So please come and join us on stage. All the volunteers, please also join us.
I think they're cleaning up or something.
All collect together.
Okay, small but mighty team. Those who lasted until the 4th day of the conference, but we were more than this.
That's how much effort it takes. You lose people on the way.
Yes, so thank you from us to you. Yes.
And of course, thank you to the video and audio team and all the people helping from the venue here as well. So thanks. A big round of applause for you as well. And not to mention Flavio and Enrique for making all those great photos that we can share later with you, so you can post them wherever you want or put them on your CV, so you really look awesome while giving that presentation at SQA. He and Enrique are responsible for that. Thank you for that.
And last but not least, thank you to you, because with more than 400 participants in person and about 600 views daily on our YouTube channel, it has been a great conference, and we're looking forward to welcome you to the next year's SQA in 2024. Thank you.